Tonight, you do not need to travel anywhere or remember anything important. You can simply rest while distant moons move quietly through the dark. Beyond our own familiar moon, hundreds of smaller worlds circle the planets in silence. Some are bright and famous, while others are barely noticed at all. Many forgotten moons have no clouds, no voices, and almost no sunlight. Yet each carries a long story written in ice, stone, dust, and gravity. There is no need to hold on to every detail. You can let the moons drift quietly through your mind. Imagine the solar system as a wide, dark ocean, with planets moving like slow ships. Around each planet, small moons follow invisible paths, some round, some tilted, some strangely stretched. A moon does not need to be large to change its world. Even a tiny moon can pull on rings, shape dust, and disturb nearby companions. Some moons resemble floating mountains rather than smooth, complete worlds. Their gravity is weak, so their ancient shapes remain uneven and softly angular. Others became round because their own weight slowly pressed them into spheres. Size changes almost everything for a moon, including its shape, warmth, and hidden activity. A larger moon can hold internal heat for much longer. That buried warmth may keep water from freezing completely beneath the silent surface. Far from the sun, this becomes one of the most surprising moon stories. A frozen exterior does not always mean a frozen interior. Europa, one of Jupiter's large moons, appears pale and smooth from a distance. Its surface is crossed by dark lines, like cracks in old porcelain. Beneath that icy shell, scientists believe a deep ocean may circle the entire moon. That ocean may contain more water than all Earth's oceans combined. Europa is not warmed mainly by sunlight, because Jupiter lies far from the sun. Instead, Europa is gently stretched by Jupiter and the gravity of nearby moons. This repeated stretching creates friction inside the moon, producing warmth over immense periods. The process is called tidal heating, though nothing about it needs to feel hurried tonight. It is a slow flexing, repeated across millions of quiet orbits. Europa's ocean may rest beneath many kilometers of ice. No sunlight reaches it, and its darkness may be older than humanity. Still, darkness does not always mean emptiness. On Earth, living communities survive around warm seafloor vents without depending directly on sunlight. Scientists therefore wonder whether Europa's ocean might also contain useful chemical energy. No evidence of life has been found there. For now, Europa remains a peaceful possibility beneath the shell of ancient ice. If your eyes feel heavy, you can let them close. The story will keep moving softly in the background. Another hidden ocean may lie inside Enceladus, a small moon of Saturn. Enceladus is much smaller than Europa, and its surface shines with clean ice. Near its south pole, long fractures open across the ground. From these fractures, water vapor and tiny ice grains rise into space. The particles form graceful plumes above the moon's bright surface. Some escape completely and spread into Saturn's broad E-ring. A small moon, therefore, helps create part of a giant planetary ring. This is one of the gentlest connections in the solar system. A moon only, about 500 kilometers wide, quietly paints ice around Saturn. Spacecraft have flown through Enceladus's plumes and measured their ingredients. They found water, salts, organic molecules, and particles linked to warm rock water reactions. These clues suggest that liquid water touches the rocky seafloor below. Enceladus may have hydrothermal activity beneath its frozen exterior. The moon looks perfectly still from above, while chemistry continues far below. Its hidden sea may be global, wrapping around the rocky center. Tidal heating keeps part of that water liquid despite the distant cold. Saturn's gravity pulls on Enceladus as the moon follows its slightly oval orbit. Each journey creates a small change in shape and a little internal warmth. Nothing about this process needs to be imagined quickly. You can picture the moon slowly breathing through its southern fractures. Farther out, Titan circles Saturn beneath a thick orange atmosphere. Titan is larger than Mercury. Although it is still considered a moon, its atmosphere is mostly nitrogen, with methane drifting through cold upper layers. Clouds gather there, rain falls, and rivers move across the surface. But Titan's rain is not made of water. Its clouds and lakes are largely made of liquid methane and ethane near Titan's poles. Dark lakes spread across broad, quiet landscapes. Some shorelines resemble coastlines seen from high above Earth. The resemblance is gentle but strange. Because the temperature is intensely cold, water ice on Titan behaves more like solid rock. Methane moves through the sky in a cycle, somewhat like Earth's water cycle. It evaporates, forms clouds, falls as rain, and gathers in rivers and lakes. Titan may also hide a salty water ocean beneath its thick crust. One moon may therefore hold two very different kinds of liquid. Hydrocarbon lakes rest on the surface, while water may remain hidden below. Titan's thick air softens the sunlight into a permanent amber haze. Someone standing there might see Saturn only faintly, if at all. The atmosphere would hide much of the sky behind layered orange mist. Titan is not forgotten because it is unimportant. It is forgotten because even famous moons contain details people rarely imagine. There is no need to hold on to every detail. You can let the moons drift quietly through your mind. Not every moon was born beside the planet it circles today. Some may have formed elsewhere, then wandered close enough to be captured. Neptune's moon. Triton is probably one of these captured worlds. Triton travels around Neptune opposite the direction of the planet's rotation. This backward path is known as a retrograde orbit. It strongly suggests that Triton formed elsewhere before Neptune's gravity captured it. Triton may once have belonged to the distant Kuiper belt. It could be related to icy worlds such as Pluto. After capture, Triton's orbit slowly became rounder through powerful tidal interactions. That long adjustment may have heated the moon deep inside. Today, Triton has one of the coldest known surfaces in the solar system. Its pale ground contains frozen nitrogen, water ice, and other frozen materials. Voyager 2 observed dark plumes rising above its surface in 1989. Weak sunlight may warm transparent nitrogen ice and build pressure beneath it. Gas then escapes through vents, carrying dark particles into the thin atmosphere. Even near the edge of the planetary system, a moon can remain quietly active. Triton also keeps nearly the same face turned toward Neptune. Above its surface, the blue planet would remain almost motionless in the sky. Around it, faint rings and tiny moons continue their distant paths. The solar system contains many smaller companions that receive far less attention. Some are only a few kilometers wide. They circle far from their planets on steep, stretched, or backward orbits. Many were probably captured, broken apart, or scattered during ancient encounters. Groups of small moons sometimes share similar paths around the same planet. They may be fragments of one larger body shattered long ago. The original moon disappeared, but its pieces preserve the memory of its orbit. Forgotten moons are often like this. They are quiet clues about events that happened billions of years before human memory. Some shape rings, some hide oceans, and some preserve the chemistry of ancient cold. Others simply continue around their planets, almost too small for us to notice. For now, Let those distant paths widen gently in your imagination. Europa moves beneath cracked ice, while Enceladus releases bright grains into Saturn's rings. Titan rests beneath orange clouds, and Triton circles backward in Neptune's blue light. You do not need to remember which moon belongs to which planet. You can let each one pass like a slow light beyond a dark window. The moons will continue their ancient journeys without needing your attention, and you can rest here, while the quiet solar system keeps moving. Beyond Europa, 3 other large moons circle Jupiter through the same deep darkness. Each has been shaped by gravity, cold, and a very different internal history. Io is the closest of Jupiter's 4 largest moons. It is also the most volcanically active world known in the solar system. Its surface is colored with yellow, orange, white, and dark patches. These colors come from sulfur compounds spread across broad volcanic plains. Io does not have oceans or thick forests of clouds. Instead, its interior is continually warmed by powerful tidal forces. Jupiter pulls strongly on Io, while Europa and Ganymede disturb its orbit. These neighboring moons keep Io's path slightly oval, rather than perfectly circular. As Io moves closer to Jupiter, the planet's gravity stretches it more strongly. As it moves farther away, the stretching becomes a little weaker. The moon bends again and again during every quiet journey around Jupiter. This constant flexing produces enough heat to melt rock deep inside. Volcanoes release lava across the surface and send tall plumes into space. Some plumes rise hundreds of kilometers above the ground. Against Jupiter's enormous presence, they would appear delicate and almost weightless. Io's volcanic activity continually renews much of its surface. Impact craters are rare because fresh material covers older marks. The moon is ancient, but many visible landscapes are surprisingly young. There is no need to hold on to every detail. You can let the moons drift quietly through your mind. Farther from Jupiter, Ganymede follows a slower and colder path. Ganymede is the largest moon in the solar system. It is even larger than the planet Mercury. If it circled the sun directly, it might easily be called a planet. Its surface contains dark, ancient regions and lighter grooved terrain. The groove suggests that the crust once stretched and shifted long ago. Beneath the ice, Ganymede may contain several layers of liquid water. Some scientific models describe water separated by different forms of high-pressure ice. Its hidden interior may resemble a layered world of rock, ocean, and frozen shells. Ganymede is also the only known moon with its own internal magnetic field. Deep inside, a liquid metallic core may still be slowly moving. This motion creates a faint magnetic bubble within Jupiter's much larger one. Auroras have been observed around Ganymede's polar regions. Their gentle movement helps scientists study the ocean hidden below. Jupiter's magnetic environment causes the auroras to shift slightly over time. The amount of movement suggests that salty water lies beneath the surface. A hidden ocean can leave clues without ever seeing the sky. Nearby, Callisto appears darker and much more heavily cratered. Its surface may be among the oldest preserved landscapes in the solar system. For billions of years, impacts have written overlapping circles across its frozen crust. Some craters are so ancient that newer craters cover their edges. Callisto seems less internally active than Europa or Ganymede. It may never have separated fully into neat internal layers. Rock and ice could remain partly mixed throughout much of its interior. Yet Callisto may also contain a buried ocean. Electrical measurements from spacecraft suggest a conductive layer beneath the crust. Salty liquid water is one possible explanation. A world can appear unchanged above, while preserving liquid far below. Callisto's old surface has remained quiet through most of solar system history. It is like a dim record kept beneath Jupiter's striped light. If your eyes feel heavy, you can let them close. The story will keep moving softly in the background. Inside the orbits of these great moons, smaller companions circle close to Jupiter. Methes, Adrastea, Amalthea, and Phoebe are easily overlooked. They move near Jupiter's faint ring system. Dust knocked from their surfaces may help maintain those delicate rings. Methes and Adrastea travel very close to the giant planet. They complete their orbits faster than Jupiter rotates from their tiny surfaces. Jupiter would fill an enormous part of the sky. Amalthea is larger, though it is still shaped irregularly. Its reddish surface may be coated by material from Io. The moon is not dense enough to be made entirely of solid rock. It may contain many empty spaces within a loosely assembled interior. Some small moons are less like solid balls and more like gentle piles of rubble. They may have formed from fragments that slowly gathered together. Their shapes preserve the weakness of their gravity. Nothing pressed them firmly into smooth spheres. Around Saturn, the variety of small moons becomes even more intricate. Some travel inside the rings, while others circle just beyond them. Their gravity creates gaps, waves, and narrow edges in the ring material. Pan moves inside the Encke gap of Saturn's. A ring. It has a rounded central body surrounded by a broad ridge. The ridge may have grown as ring particles settled onto the moon. Pan sometimes resembles a small walnut drifting through ice. Atlas, another tiny moon, carries a similar ridge around its middle. Both worlds have gathered material from the rings they travel beside. They show that a moon shape can be influenced by its surroundings. Daphnis moves through the narrow Keeler gap. Its gravity pulls on nearby ring particles and creates vertical waves. Near the time of Saturn's equinox, those waves cast long shadows across the rings. The shadows reveal structures that are otherwise difficult to see. A moon, only a few kilometers wide, can shape patterns across great distances. These small bodies are sometimes called shepherd moons. They guide ring particles through gravity rather than touch. Prometheus and Pandora travel near Saturn's narrow F-ring. Prometheus passes close enough to draw streamers from the ring's dusty material. Each passage produces curved patterns that slowly change and fade. The ring never becomes completely still. It responds softly to the repeated pull of nearby moons. Two other Saturnian moons perform an especially unusual orbital exchange. Janus and Epimetheus travel on paths separated by only a small distance. They cannot pass one another in the ordinary way. Every few years, their mutual gravity changes both orbits. The inner moon moves outward, while the outer moon moves inward. They gently exchange places without colliding. This slow celestial dance is unlike any ordinary pair of moons. Their paths demonstrate how gravity can create order from apparent closeness. Farther away, Mimas circles Saturn with a heavily cratered surface. Its largest crater, Herschel, covers a remarkable part of the moon. The impact changed Mimas greatly, but did not break it apart. For years, Mimas was considered a completely frozen and inactive body. More recent measurements suggest its motion may be more complicated. One possible explanation is a hidden ocean beneath its icy shell. The evidence is still being studied and interpreted. Even a moon long considered quiet may contain an unseen interior story. Tethys, another icy moon, carries a vast canyon called Ithaca Chasma. The canyon stretches across much of the moon's surface. It may have formed when the interior froze and expanded. As water becomes ice, it occupies slightly more space. The crust may have cracked as the moon's hidden ocean gradually solidified. Tethys is mostly water ice and reflects sunlight very efficiently. From a distance, it appears pale and calm against Saturn's shadow. Dione has bright streaks crossing its darker regions. Early observers thought these markings might be deposits of frost. Closer images revealed cliffs, fractures, and long icy scarps. Some features formed when the crust broke and shifted. Dione may also hide a liquid layer beneath its surface. Its internal heat is weaker than Enceladus's, yet perhaps not entirely gone. Rhea, Saturn's second largest moon, is another ancient icy world. Its surface is marked by craters and long, bright fractures. A thin atmosphere of oxygen and carbon dioxide has been detected around it. The atmosphere is extremely faint and could never resemble Earth's air. Radiation may release oxygen from water ice on the surface. Even frozen ground can create a delicate veil of molecules around a moon. There is no need to hold on to every detail. You can let the moons drift quietly through your mind. Iapetus travels much farther from Saturn than most large inner moons. One side of Iapetus is dark, while much of the other side is bright. The contrast made the moon appear to change brightness during early observations. Dark dust from distant moons may settle onto its leading side. Sunlight then warms darker areas more efficiently. Ice slowly moves away from warmer regions and gathers in colder places. Over time, this process may have strengthened the difference between both sides. Iapetus also has a remarkable ridge running along much of its equator. The ridge rises several kilometers above the surrounding terrain. Its origin remains uncertain. It may have formed from internal forces or fallen material from a vanished ring. Some mysteries remain gentle precisely because they are not yet solved. Nearby in the broad Saturnian system, Hyperion tumbles in an unpredictable way. It is irregular, porous, and covered with deep craters. Its low density suggests a large amount of empty space inside. Hyperion may be a fragment of a larger moon broken apart long ago. Unlike most large moons, it does not keep one face towards Saturn. Its rotation changes because of its unusual shape and gravitational interactions. This motion is chaotic, though not hurried. Across long spans of time, the moon turns in shifting and uncertain patterns. Its surface has been compared to a sponge because of its deep, sharp-edged craters. Dark material collects inside many crater floors. Sunlight warms these deposits and may deepen the hollows around them. Even this strange little world follows a quiet rhythm through Saturn's distant light. Some moons are remembered because they are large. Others matter because they preserve small clues about rings, oceans, and ancient collisions. A tiny moon may sculpt a gap. An icy moon may hide an ocean. A captured fragment may carry material from a distant region of the solar system. Together, they reveal that planets are never truly alone. Their moons exchange dust, gravity, heat, and orbital energy across immense time. You can picture Jupiter with its crowded family moving through darkness. Then Saturn appears farther away, surrounded by rings and countless small companions. Nothing needs to happen quickly in this part of the sky. The moons continue circling, shaping their planets through patient repetition. And while their paths continue, you can allow your thoughts to become quieter. The distant worlds will keep moving softly, even as you drift closer to sleep. Far beyond Saturn, Uranus travels through a quieter and dimmer region of the solar system. Its moons move beneath pale blue light, where sunlight feels distant and gentle. Uranus is unusual because the planet rotates almost completely on its side. Its moons follow the same tilted system around the planet's equator. From far away, the whole family can appear like a wheel turning through space. The 5 largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon. Their names come from old plays and poems rather than ancient mythology. Each one carries a different arrangement of ice, rock, craters, and fractures. Miranda is the smallest of the 5 large Uranian moons, yet its surface may be the most visually surprising. Enormous cliffs, ridges, valleys, and patchwork regions cover the frozen landscape. Some areas look as though separate pieces were gently fitted together. One old idea suggested Miranda was broken apart and later reassembled. Scientists now think internal heating may better explain many of its strange features. Tidal forces could once have warmed and reshaped parts of the moon. Miranda's orbit may have changed through interactions with neighboring moons. Those changes could have increased internal flexing for a time. The heating eventually weakened, leaving the surface frozen in its unusual form. Today, Miranda is quiet, but its cliffs preserve an active ancient past. One of its great scarps rises far higher than most cliffs on Earth. Because Miranda's gravity is weak, a falling object would descend very slowly. The landscape would feel enormous. While every movement remains strangely light, there is no need to hold on to every detail. You can let the moons drift quietly through your mind. Ariel has a brighter and smoother surface than many nearby moons. Long valleys and fault systems cross its icy crust. Some channels may have carried mixtures of ice and warmer material. The moon may once have experienced cryovolcanism. Instead of molten rock, cryovolcanoes release water, ice, or other cold materials. Ariel's relatively young terrain suggests that its interior stayed warm for some time. It may still hide a deep layer of liquid water. No spacecraft has yet returned to study Ariel closely since Voyager 2. Much of this moon remains known through images gathered during one distant passage. Umbriel is darker and more heavily cratered. Its surface reflects less sunlight than Ariel's bright ice. One of its most curious features is a bright ring inside a large crater. The ring may be exposed ice or material created during an ancient impact. Umbriel appears quiet, even among the quiet moons of Uranus. Its old surface may have changed little for billions of years. Titania is the largest moon of Uranus. A vast network of canyons cuts across its surface. These fractures may have formed as the moon's interior cooled and expanded. If an underground ocean once froze, the growing ice could have stretched the crust. Some models suggest that a liquid layer may still remain deep inside. Titania's distant orbit receives only weak sunlight. Yet radioactive elements within its rocky interior may provide lingering warmth. Oberon, the outermost large moon, is also covered with ancient craters. Dark material rests on the floors of several impact basins. A high mountain rises near the edge of images returned by Voyager 2. Its full shape remains uncertain because the spacecraft saw only part of the moon. Oberon may also contain a buried ocean beneath many layers of ice. The Uranian moons are easy to forget because they have been visited only once. Voyager 2 passed them in January 1986. The encounter lasted only a short time compared with their immense histories. Since then, the moons have continued circling without another close visitor. Their seasons are also unusual because Uranus is tilted so greatly. For many years, one hemisphere can face prolonged sunlight. Then, darkness slowly returns for an equally long season. The moons pass through these changes in a patient rhythm. Their frozen surfaces brighten and fade beneath the distant sun. Farther outward, Neptune's moons form another scattered family. Triton dominates the system, but many smaller moons travel around it. Nereid follows one of the most stretched orbits of any known moon. Sometimes it moves much closer to Neptune. At other times, it travels far into the surrounding darkness. Its orbit may have been disturbed when Triton was captured. Before Triton arrived, Neptune may have had a more orderly moon system. The capture could have scattered, destroyed, or rearranged many earlier moons. Nereid may be a survivor from that ancient disturbance. Its irregular orbit preserves a memory of Neptune's changing family. Proteus is Neptune's second largest moon. It is dark, irregular, and nearly large enough to become round. A huge crater called Pharos marks much of one side. The impact came close to breaking the moon apart. Proteus remained whole, carrying the crater through countless later orbits. For a long time, astronomers did not discover Proteus because it circles close to Neptune. The planet's brightness hid the dark moon and nearby glare. It was finally identified in images from Voyager 2. Sometimes, a moon is forgotten simply because its planet shines more brightly. Neptune also has a small moon called Hippocamp. It circles near the larger moon. Proteus. Hippocamp may be a fragment knocked from Proteus during a past collision. A crater on Proteus could be connected to the smaller moon's origin. The idea is not certain, but it forms a gentle possibility. One moon may have carried another moon into existence through scattered debris. Nearby, Naiad and Thalassa follow remarkably close orbits. Their paths are arranged so they avoid meeting. Naiad moves above and below Thalassa's orbital plane in a repeating pattern. From one viewpoint, the motion resembles a slow wave around Neptune. The two moons come near each other without colliding. Gravity keeps their movements carefully synchronized. This arrangement is sometimes described as a dance of avoidance. Even tiny moons can follow beautifully organized paths. If your eyes feel heavy, you can let them close. The story will keep moving softly in the background. Closer to the Sun, Mars has only two small moons. Phobos and Deimos look more like captured asteroids than round worlds. Both are dark, irregular, and covered with impact marks. Phobos circles extremely close to Mars. It completes an orbit in less than 8 hours. Because it moves faster than Mars rotates, it rises in the west. It then crosses the sky and sets in the east. From the Martian surface, Phobos would move surprisingly quickly among the stars. Yet from far away, its orbit remains part of a slow celestial pattern. Phobos is gradually moving closer to Mars. Tidal forces reduce its orbital distance by a small amount over time. In tens of millions of years, it may break apart or reach the planet. The fragments could briefly form a ring around Mars. This change lies so far in the future that it carries no urgency tonight. For now, Phobos continues along the same familiar path. Its largest crater, Stickney, covers a large part of the moon. Long grooves extend across the surface around it. Some grooves may come from impacts or from debris orbiting Mars. Others may reflect stress within the small moon. Phobos also contains many empty spaces between loosely connected materials. It may be a rubble pile held together by weak gravity. Deimos circles much farther from Mars. It moves more slowly and appears calmer in the Martian sky. Its surface is covered with a thick layer of dusty material. This dust softens the outlines of many craters. Deimos may resemble a dark stone resting beneath a veil of powder. The origins of both Martian moons remain uncertain. They may be captured asteroids from a nearby region. They may also have formed from debris after a large impact on Mars. Future samples could help distinguish between these possibilities. A moon's chemistry can reveal where it began. Some moons travel in pairs that share a single orbital region. Saturn's moons, Telesto and Calypso, accompany the larger moon. Tethys. They rest near stable gravitational points along Tethys's orbit. These locations are called Lagrange points. At such points, gravity allows small bodies to remain in balanced positions. Helene and Polydeuces similarly share the orbit of Dione. They are known as Trojan moons. The word Trojan is also used for asteroids sharing planetary orbits. These small moons do not follow directly beside their larger companions. Instead, they travel ahead or behind at steady angular distances. Their positions are maintained by the combined gravity of Saturn and the larger moon. The arrangement is delicate, yet it can last for very long periods. Some forgotten moons are discovered only as tiny points of light. Astronomers take repeated images and compare the positions of faint objects. A moving point may reveal a moon traveling around a distant planet. Its orbit must then be measured over months or years. Many outer moons have highly tilted and backward paths. These irregular satellites probably did not form in their current locations. They may be captured asteroids or fragments of larger captured bodies. Jupiter, Saturn, Uranus, and Neptune all possess groups of such moons. Members of each group often share similar colors and orbital directions. This suggests that one captured object may have broken into many pieces. The fragments now travel as distant families around their planet. They are separated by millions of kilometers, yet still share an ancient origin. Their names are often unfamiliar because discoveries continue gradually. Some remain unnamed for years, while their orbits are confirmed. A temporary designation may be their only identity at first. The designation records the year of discovery and the planet they orbit. Later, an official name may connect them with mythology or literature. Until then, they continue moving without needing a familiar name. There is something peaceful in that. The world does not become real only when people notice it. It does not need a famous story to continue circling its planet. Our own moon may also have begun through an ancient transformation. The leading explanation involves a collision early in Earth's history. A young planetary body struck the growing Earth billions of years ago. Material from the impact spread into orbit. That orbiting material gradually gathered into the moon. The process was enormous, but it belongs to a distant and quiet past. Over time, the newborn moon was much closer to Earth. It appeared larger in the sky and moved more rapidly. Tidal interactions slowly carried it outward. Even today, the moon moves away by a few centimeters each year. At the same time, Earth's rotation gradually becomes slower. The length of a day has changed across geological time. Ancient corals preserve growth patterns connected to shorter days. Long ago, a year contained more individual days than it does now. The moon also stabilizes Earth's axial tilt. Without it, Earth's orientation might vary more dramatically over long periods. That stability has influenced the rhythm of seasons and climate. The moon shapes ocean tides, but it also affects the solid Earth. Land rises and falls slightly under lunar and solar gravity. These movements are much smaller than ocean tides. Still, the entire planet responds gently to the moon's presence. Moons can influence planets without making any sound. They pull on oceans, rings, crusts, atmospheres in rotation. They can warm hidden interiors or keep orbital systems in balance. A large moon may help stabilize a planet. A small moon may sweep dust from a ring gap. A captured moon may rearrange an entire planetary family. You can let these connections remain soft and unfinished. There is no need to remember every name or every orbit. Imagine Uranus turning on its side beneath its pale atmosphere. Its 5 large moons move around it like distant lanterns. Beyond them, Neptune holds Triton, Nereid, Proteus, and many smaller companions. Closer inward, Phobos crosses the Martian sky, while Deimos follows more slowly. Near Saturn, tiny Trojan moons rest in balanced places along invisible paths. The solar system is filled with worlds that rarely enter ordinary conversation. They continue through darkness, patient and unobserved. You can let them pass quietly through your thoughts. The moons will keep their ancient paths, while your mind becomes still. Beyond Neptune, the sun becomes a small and distant source of light. Here, icy worlds travel through the broad darkness of the Kuiper Belt. Pluto is accompanied by 5 known moons. The largest, Charon, is unusually big compared with the world it circles. Charon is about half Pluto's diameter. Because of this, Pluto and Charon behave almost like a double world. They orbit a point located outside Pluto's surface. Both bodies turn around the shared center of gravity. Pluto always shows the same face to Charon. Charon also keeps the same face turned toward Pluto. From one surface, the other world would remain fixed in the sky. It would never rise or set in the familiar way. Instead, it would hang above one region for every long day. Other parts of each world would never see their companion at all. There is no need to hold on to every detail. You can let these distant moons move quietly through your mind. Charon's northern region appears darker than much of its surface. This reddish area is sometimes called Mordor Macula. Material escaping from Pluto may drift toward Charon and settle near its poles. Sunlight then slowly changes the chemistry of these frozen molecules. The result is a dark cap formed partly from material shared between worlds. Even in the cold Kuiper Belt, one body can gently color another. Charon also carries deep canyons across its icy landscape. Some stretch for hundreds of kilometers. They may have formed when an ancient internal ocean froze and expanded. The growing ice could have stretched the surface until it cracked. A smooth plain called Vulcan Planitia covers part of one hemisphere. It may have been resurfaced by cold, slushy material from the interior. This process is another possible form of cryovolcanism. The world appears frozen now, but its surface remembers warmer conditions. Pluto's 4 smaller moons are Styx, Nix, Kerberos, and Hydra. They circle outside Charon on carefully arranged paths. These moons are irregular rather than round. Their weak gravity cannot reshape them into smooth spheres. Nix is elongated and reflects light from a surface rich in water ice. Hydra is also bright and may be covered with relatively clean ice. Kerberos is darker than scientists originally expected. It may have formed from fragments with a different surface composition. Styx is the smallest and faintest of Pluto's known moons. Its shape is known only through distant spacecraft images. All 4 small moons rotate in unusual ways. Instead of keeping one face toward Pluto, they tumble as they orbit. The combined gravity of Pluto and Charon disturbs their rotation. Their turning can be irregular and difficult to predict far ahead. Yet the motion is not restless in a human sense. It unfolds across long, silent journeys through cold sunlight. The small moons also follow orbital rhythms connected with Haron. Their periods are close to simple numerical relationships. These patterns may preserve clues about how the entire system formed. A giant impact may have created Pluto's moons. Debris from the collision could have gathered into Charon and the smaller companions. This resembles the leading explanation for the origin of Earth's moon. But every collision leaves a different family behind. Some create one large moon. Others create several small worlds moving together. Farther through the Kuiper Belt, other dwarf planets also have moons. Eris is accompanied by a small moon called Dysnomia. Observing Dysnomia helps scientists calculate the mass of Eris. A moon's orbit reveals the strength of the gravity pulling it inward. From this motion, the hidden weight of the central world can be estimated. Dysnomia follows a distant path around Eris. Both worlds travel far beyond Pluto for much of their solar orbit. Sunlight. There is hundreds of times weaker than on Earth. The sun would still be the brightest object in the sky, but it would appear more like an intense star than a warming disk. Makemake has a small moon, informally known by its discovery designation. It was found as a faint point near the brighter dwarf planet. Before its discovery, Makemake's unusual thermal measurements were difficult to explain. A dark moon may have contributed some of the detected warmth. Amora P. The tiny companion therefore helped clarify observations of the larger body. Many moons reveal themselves indirectly. They change brightness, pull on their planets, or block distant starlight. Haumea, another dwarf planet, has two moons named Hiyaka and Namaka. Haumea rotates exceptionally quickly. Its fast spin stretches the dwarf planet into an elongated shape. Hiyaka is the larger and more distant moon. Its surface contains strong signs of crystalline water ice. Namaka travels closer to Haumea on a more complicated orbit. The two moons influence each other through gravity. Their paths may shift slowly over time. Haumea also possesses a narrow ring. The ring, moons, and nearby icy objects may share an ancient origin. Long ago, a collision may have broken material from Haumea. Some fragments escaped into independent orbits around the Sun. Others remained nearby and became moons. A distant family of worlds may therefore be pieces of one forgotten event. If your eyes feel heavy, you can let them close. The story will keep moving softly in the background. Moons are not found only around planets and dwarf planets. Some asteroids also carry tiny companions. The asteroid Ida was the first asteroid found to have a moon. Its small companion is called Dactyl. Dactyl is only about 1 kilometer across. It was discovered when the Galileo spacecraft passed Ida in 1993. Before that encounter, asteroid moons were mostly theoretical possibilities. Now, many asteroids are known to have one or more satellites. Some small asteroids are actually binary systems. Two bodies of similar size circle a shared center of gravity. Others contain one larger object and a much smaller moon. These companions may form after collisions. They may also appear when sunlight slowly changes an asteroid's rotation. Sunlight carries momentum, although its pressure is extremely weak. Across millions of years, uneven heating can make an asteroid spin faster. If the rotation becomes too rapid, loose material may drift away. That material can gather into a small moon. A companion may therefore form without one dramatic impact. It can emerge gradually from dust and stones, leaving a spinning body. The near-Earth asteroid Didymos has a moon called Dimorphos. Dimorphos circles the larger asteroid at a very close distance. A spacecraft intentionally struck Dimorphos to test asteroid deflection. The impact slightly changed the moon's orbital period. This allowed scientists to measure how a small collision alters a binary system. Dimorphos remains in orbit, now following a somewhat changed path. Its surface is covered with rocks and loose material. Images showed a world assembled from many irregular fragments. Gravity holds them together very gently. Another asteroid, Sylvia, has two known moons. They are named Romulus and Remus. Their orbits helped reveal that Sylvia has a low average density. The asteroid may contain large empty spaces within its interior. It could be another rubble pile rather than one solid piece of rock. Cleopatra is a strangely shaped asteroid with two moons. Its long form has sometimes been compared to a dog bone. The moons Alexelios and Cleoselene follow paths around its uneven body. Their existence may be connected to Cleopatra's rapid rotation. Even oddly shaped objects can support stable moon systems. These miniature systems repeat patterns seen around giant planets. There are central bodies, satellites, orbital resonances, and shared histories. The scale is smaller, but the gravitational story remains familiar. Mars itself may have acquired Phobos and Deimos through a similar debris process. Some researchers suggest a larger moon once circled Mars. That moon may have broken apart and formed a ring. Material from the ring could have gathered into later generations of moons. Phobos may be one of the final members of this repeating cycle. The evidence is not yet complete. Moon formation often leaves several possible stories for scientists to compare. Some planetary rings may also be temporary stages in moon formation. A ring can spread, come together, or be disturbed by existing moons. Beyond a planet's Roche limit, particles can gather more easily. Inside that boundary, tidal forces may prevent a large moon from forming. Saturn's rings lie mostly within this region. Small moons near the ring edges may have collected material beyond it. Their unusual equatorial ridges could be traces of this gradual growth. A ring may slowly create moons. A moon may also slowly create a ring. When micrometeoroids strike a small icy moon, dust can escape its weak gravity. That dust spreads along the moon's orbit. Jupiter's faint rings are replenished partly by this process. Saturn's E-ring receives fresh ice from Enceladus. Neptune's narrow ring arcs may be maintained by nearby moon gravity. The boundary between a moon and a ring is not always permanent. Material moves between them across long spans of time. There is no need to remember every name. You can let the worlds become simple shapes, moving through distant light. Some of the smallest moons are discovered around objects called centaurs. Centaurs travel between the giant planets on unstable solar orbits. They may have come inward from the Kuiper belt. The centaur Chariklo has rings rather than a confirmed moon. Another centaur, likely related to icy outer bodies, may hide companions too faint to see. Small moons can remain undiscovered for decades. They may be dark, distant, and close to brighter objects. Astronomers often search for them when a distant world passes before a star. This event is called an occultation. The central body blocks the starlight for a short time. A smaller dip before or after may reveal a ring or moon. Carefully timed observations from many locations can outline the hidden system. For a few seconds, a forgotten moon may announce itself through darkness. Moons can also be found when they pull gently on one another. An unexplained wobble may suggest an unseen companion. Changes in an orbit can reveal gravity from something too faint to photograph. This method has been used throughout astronomy. Invisible objects become known through the motion they create. Long before Neptune was photographed, its gravity revealed its presence. The same principle can point towards small moons, beyond our solar system. Possible moons may circle distant planets. These are known as exomoons. No exomoon has yet been confirmed beyond serious scientific debate. Finding one is much harder than finding an exoplanet. A moon is smaller, dimmer, and often hidden beside its planet. Still, astronomers search for subtle changes during planetary transits. When a planet crosses its star, the star's light dims slightly. A large moon could create an additional, smaller dip. It might also pull the planet ahead or behind its expected schedule. These changes are called transit timing variations. The moon could also shift the length or shape of each transit. A moon and planet move around their shared center of gravity. That motion can leave a delicate pattern in repeated observations. Several candidates have attracted attention, but stellar activity and measurement noise can imitate similar signals. For now, exomoons remain possible worlds rather than confirmed discoveries. They may be common around giant planets. Some could be larger than Mars. A few might possess atmospheres, oceans, or magnetic fields. A moon orbiting a gas giant could receive light from several sources. Its star would illuminate the surface. The nearby planet might reflect additional light. The planet could also glow with heat. Especially in a young system, eclipses would bring regular periods of shadow. Tidal heating might warm the interior. A distant moon could therefore remain active even far from its star. Some exomoons may resemble Europa or Enceladus. Others may be rocky worlds with thick atmospheres. A very large moon could appear almost planet-like. From its surface, the parent planet would dominate the sky. Cloud bands and storms might fill the horizon. Other moons could appear as moving points around the same giant world. The view would be unfamiliar, yet governed by the same quiet gravity. You can let those unconfirmed moons remain softly imagined. There is no need for them to become clear tonight. Perhaps countless forgotten satellites circle planets across the galaxy. Some may hide beneath ice. Some may carry orange skies or dark hydrocarbon lakes. Others may be nothing more than small stones following ancient orbits. They do not know whether anyone has discovered them. Their paths continue without names, maps, or visitors. In the distant Kuiper Belt, Charon remains fixed above one side of Pluto. Nix and Hydra tumble through the faint light beyond it. Around Haumea, two icy moons preserve traces of an ancient collision. Near small asteroids, tiny companions circle worlds barely held together. And somewhere beyond the sun, possible moons may cross distant stars. You can allow all these worlds to become quieter now. Let their orbits widen into the darkness behind your thoughts. The smallest moons will keep circling. The farthest moons will remain beneath their patient stars, and you can rest while the forgotten stories move softly onward. A moon can be forgotten, even while it quietly shapes an entire planetary system. Its influence may appear in tides, rings, rotation, atmosphere, and hidden heat. Gravity works across empty space without needing sound or visible contact. Every moon pulls on its planet, and every planet pulls back. The stronger pull raises a small bulge in the planet's material. On Earth, this is easiest to notice in the oceans. Water rises slightly on the side facing the moon. Another tidal bulge forms on the opposite side of Earth. As the planet rotates beneath them, coastlines experience changing water levels. The sun also contributes to Earth's tides. When the sun, earth, and moon line up, their poles work together. These alignments create stronger spring tides. The name comes from the idea of water springing outward. It is not connected to the season of spring. When the sun and moon pull from different directions, tides become gentler. These are called neap tides. The entire cycle follows the moon through its familiar phases. There is no need to hold on to every detail. You can let the moons drift quietly through your mind. Tides do more than move water along shorelines. They also transfer energy between a planet and its moon. Earth rotates much faster than the moon travels around it. The tidal bulges are carried slightly ahead of the moon's position. Their gravity pulls the moon forward along its orbit. This extra pull gradually sends the moon farther from Earth. At the same time, Earth loses a little rotational energy. Our days become longer by a very small amount, across hundreds of millions of years. Those tiny changes become meaningful. Ancient Earth once rotated more quickly. The moon once appeared much larger in the sky. Tidal patterns were stronger because the two worlds were closer. The moon has continued moving outward through nearly all recorded geological time. Eventually, very far in the future, the relationship will change again. But tonight, the moon remains close enough to guide oceans and brighten nights. Other planet-moon systems exchange energy in similar ways. Mars rotates faster than its inner moon. Phobos travels around the planet, but Phobos orbits so close that it moves around Mars faster than Mars turns. This reverses the direction of tidal energy transfer. Instead of moving outward, Phobos slowly spirals inward. Deimos travels farther away, and follows the more familiar hour pattern. 2 moons around. One planet can therefore evolve in opposite directions. Jupiter's moon. Io also exchanges energy through tides. Its slightly oval orbit is maintained by neighboring moons. Without their influence, tidal forces might slowly make Io's orbit more circular. A circular orbit would reduce the repeated stretching inside the moon. Its volcanic activity might then become weaker. But Europa and Ganymede continually disturb Io's path. The 3 moons are connected through an orbital resonance. For every orbit completed by Ganymede, Europa completes about 2. During the same time, Io completes about 4. Their positions repeat in a steady gravitational rhythm. This resonance prevents the moons from settling into simpler orbits. It keeps energy moving through the system. Io stays warm enough for widespread volcanism. Europa remains flexed enough to support a hidden ocean. Ganymede also carries traces of internal heating from its long history. 3 separate moons share one connected pattern. Their stories cannot be understood completely in isolation. If your eyes feel heavy, you can let them close. The story will keep moving softly in the background. Orbital resonance appears in many moon systems. Saturn's moons, Mimas and Tethys, share a repeating gravitational relationship. Enceladus and Dione are also connected through resonance. This connection helps maintain Enceladus's slightly oval orbit. That small difference provides the tidal flexing that warms its interior. Without Dione, Enceladus might have become colder and quieter. A larger moon can therefore help keep a smaller moon active. Hyperion and Titan also share an orbital resonance. Titan's gravity contributes to Hyperion's unusual rotation. The irregular moon tumbles, instead of showing one fixed face towards Saturn. Its changing spin is influenced by shape, orbit, and repeated gravitational pulls. Nothing in this system moves entirely alone. Each body participates in a wider arrangement. Resonance can also protect moons from dangerous close encounters. Neptune's small inner moons follow carefully timed paths. Their orbital patterns help them avoid occupying the same place together. Some moons move above and below one another. Others pass at different times through nearby regions. The gravity creates order across many repeated orbits. A system may appear crowded while remaining stable. Stability does not always mean that every distance remains unchanged. Orbits can gently shift, precess, and exchange energy. The overall pattern survives. While individual details slowly move, some moons also influence a planet's rings through resonance. A moon does not need to travel beside a ring to shape it. Its repeated gravitational pull can create gaps or waves from far away. Saturn's Cassini division is influenced partly by the moon. Mimas. Particles in that region would orbit Saturn twice for each orbit of Mimas. Repeated tugs disturb their paths. Over time, many particles are removed from the area. The result is a broad, dark gap visible from Earth. Other resonances create delicate spiral waves within Saturn's rings. The waves carry information about moon masses and ring density. Scientists can read them almost like patterns written across water. Some ring waves are created by moons outside the rings. Others may be caused by oscillations inside Saturn itself. The rings therefore record both the planet and its moons. Small shepherd moons maintain sharp ring edges. Their gravity pushes particles back toward narrow regions. Without these moons, some rings might spread more widely. The moons do not guide every particle individually. They create a repeating influence that slowly shapes the whole ring. There is no need to remember every resonance. You can let each pattern become a quiet rhythm in the dark. Moons can also affect planetary atmospheres. Titan's thick atmosphere is partly protected by its own gravity and cold temperature. But Saturn's environment still interacts with its upper layers. Molecules can escape and spread along Titan's orbit. Some material may become part of Saturn's broader magnetosphere. Io supplies an even larger cloud of particles around Jupiter. Volcanic gases escape from Io and become electrically charged. These ions form a vast ring called the Eoplasma torus. It follows Io's orbit around Jupiter. Jupiter's magnetic field sweeps this material through space. Electrical currents connect Io with Jupiter's upper atmosphere. Auroral spots appear where these currents enter the planet. Smaller footprints are also associated with Europa and Ganymede. A moon can therefore leave a glowing mark in its planet's sky. From Jupiter's cloud tops, these auroral features would move with the moons. The distant satellites write their presence into the planet's atmosphere. Enceladus similarly adds water-rich material to Saturn's environment. Its plumes feed the E-ring. Some water molecules eventually reach Saturn's upper atmosphere. A tiny moon can influence chemistry around a planet far larger than itself. Moon material can also travel between neighboring moons. Dust ejected from one surface may land on another. Saturn's moon. Iapetus likely gathers dark particles from outer irregular moons. Phoebe is one possible source. Phoebe travels around Saturn in a backward direction. It is dark, irregular, and probably captured from the outer solar system. Dust escaping Phoebe spreads into an enormous, faint ring. The ring is far too dim to see with ordinary eyes. Its particles move inward over time. Iapetus sweeps through some of this dark material. The leading side becomes coated more heavily. Sunlight then strengthens the contrast between dark and bright regions. A small captured moon may therefore help create the unusual face of a larger one. Jupiter's outer moons may exchange material in similar ways. Impacts lift dust from their weak surfaces. The particles can drift, collide, or settle elsewhere. A moon's surface may contain traces of another world. Even distant satellites are not completely isolated. Moons also create eclipses. When a moon passes into its planet's shadow, sunlight briefly disappears. For an observer on the moon, the planet would cover the sun. The sky might darken while the planet's atmosphere glowed around its edge. On worlds without atmospheres, shadows would appear especially sharp. Jupiter's large moons experience eclipses during many of their orbits. Their brightness changes as they enter and leave Jupiter's shadow. These events help transform our understanding of the universe. In the 17th century, astronomers carefully timed Io's eclipses. The observed times changed depending on Earth's distance from Jupiter. When Earth was farther away, the eclipse appeared later. This delay helped reveal that light travels at a finite speed. A forgotten moon helped measure something fundamental about the universe. Galileo's discovery of Jupiter's large moons also changed humanity's view of space. They showed that not everything circled Earth. A planet could have its own family of companions. The observation supported a wider, less Earth-centered universe. Today, these moons are familiar to astronomers, but the idea they revealed remains quietly profound. There are many centers of motion in the cosmos. A moon can also pass in front of its planet from our viewpoint. Its shadow moves across the planet's cloud tops. On Jupiter, several moon shadows may sometimes appear at once. Each shadow is a small dark circle, moving over enormous storms. The moon itself may be visible nearby as a bright point. On Saturn, Titan casts a broad shadow during suitable seasons. Smaller moons create subtler crossings. Uranus and Neptune also receive moon shadows, but their distant positions make such events difficult to observe. From the surface of another moon, eclipses could become part of the landscape. Europa would often see Jupiter covering a large portion of the sky. The giant planet appears many times wider than Earth's moon appears to us. Jupiter's shadow can cool Europa's surface for a short time. The moon then returns to sunlight and warms again slightly. These repeated changes may affect the shallowest layers of ice. Titan also experiences periods inside Saturn's shadow. Its thick atmosphere responds more gradually to changing light. Haze softens the transition between brightness and darkness. The sun would fade behind Saturn's enormous disk. Then it would return to Titan's orange sky. Some moons never experience eclipses because their orbits are highly tilted. Others enter shadow only during certain planetary seasons. A moon's orbital angle determines the rhythm of its darkness. The story will keep moving softly in the background. You do not need to follow every shadow. Some planets temporarily capture small objects as moons. These companions are sometimes called minimoons. Earth occasionally captures a small asteroid for months or years. The object follows a complicated path through the Earth. Moon system. It may circle Earth only a few times before escaping. These objects are usually only a few meters across. They are extremely faint and difficult to detect. One temporary satellite was designated 2006 RH-20. It remained near Earth for roughly a year before returning to solar orbit. Another object, 2020 CD3, was discovered after being captured for several years. It was no longer bound to Earth by the time detailed studies were completed. Temporary moons show that capture is not always permanent. Gravity can hold a small object briefly, then release it again. The border between a moon and an asteroid can therefore become uncertain. Some objects called quasi-satellites appear to travel around Earth. In reality, they orbit the Sun rather than Earth. Their motion keeps them near our planet for long periods. From Earth, their paths can resemble wide loops. They are companions without being true moons. The asteroid Kamo-Aliwa is one such object. It may even contain material connected to the moon. Some studies suggest it could be a fragment ejected by an ancient lunar impact. The idea remains under investigation. If true, a piece of the moon may now circle the Sun beside Earth. It would be neither an ordinary asteroid nor a true satellite. It would be a distant remnant following a related path. Other planets may also capture temporary moons. Jupiter's enormous gravity can redirect comets and asteroids. Some remain briefly before escaping or colliding. The giant planet's irregular moon population may include survivors of older captures. Saturn, Uranus, and Neptune likely experienced similar events. During the early solar system, capture was probably more common. Planets moved through dense fields of leftover material. Close encounters changed countless orbits. Some objects were thrown outward. Others fell inward or remained as moons. The modern solar system is calmer than it once was, but small captures still occur in the background. A forgotten moon may exist for only a short chapter of time. It arrives without ceremony and leaves without being noticed. There is something peaceful in such temporary companionship. Not every orbit needs to last forever. Some moons may have disappeared entirely. They could have collided, broken apart, or fallen into their planets. Their former presence may survive in rings or unusual crater patterns. Mars may have lost earlier generations of moons. Saturn's rings may include material from a destroyed icy body. Uranus's rings and inner moons may have been rebuilt after collisions. Neptune's original moons may have been disrupted by Triton's capture. A missing moon can still shape the system that remains. Scientists study gaps, dust, and orbital irregularities for these clues. A planet's present family may be only the latest arrangement. Moons form, migrate, break, gather, and exchange places over deep time. The systems we see today are not finished. They are quiet moments within much longer histories. Our own moon also preserves traces of lost material. Its surface is covered by craters from objects that no longer exist nearby. Some impacts created vast basins, later filled by dark volcanic plains. Other impacts launched lunar rocks into space. A few of those rocks eventually reached Earth as meteorites. Fragments of the moon now rest in museums and laboratories. Some may remain hidden among ordinary stones in deserts or ice fields. Material has traveled between Earth and the moon in both directions. Large impacts on Earth may have sent terrestrial rocks into lunar space. A small number could have landed on the moon and remained preserved. The moon may hold pieces of ancient Earth no longer found here. Its dry surface could protect records erased by our active geology. A moon can therefore become an archive for its planet. It stores impact history, solar radiation, and particles from space. The far side of Earth's moon is especially quiet from human radio signals. The moon's solid body blocks transmissions from Earth. For this reason, the far side is considered valuable for radio astronomy. A telescope there could listen to faint signals from the early universe. It would observe without the constant interference created by modern technology. The moon may someday help us hear more distant parts of cosmic history. For now, it continues its slow rotation around Earth. One side remains familiar, marked by dark plains and bright highlands. The other carries more craters and fewer large volcanic basins. Both sides belong to the same quiet companion. You can let all these influences fade into one gentle idea. Moons are not merely objects beside planets. They are participants in planetary lives. They raise tides, create heat, guide rings, carry dust, and shape rotation. They can illuminate atmospheres with auroral footprints. They can preserve ancient records or briefly join a planet before drifting away. Some remain for billions of years. Others stay only for a few quiet orbits. Nothing needs to be remembered clearly. Imagine Io crossing Jupiter's shadow. Imagine Enceladus adding bright ice to Saturn's rings. Picture a tiny asteroid temporarily circling Earth before returning to the Sun. Farther away, a lost moon may survive only as dust around a planet. All these paths continue through a darkness that is never truly empty. Gravity connects each world with another. And while those gentle connections continue, your thoughts can become lighter. The moons will hold their planets softly. The planets will carry their moons through the night, and you can rest beneath their distant, patient motion. Some moons preserve time more clearly than almost any landscape on Earth. Their surfaces remain exposed to space for millions or even billions of years. Without rain, rivers, forests, or moving continents, old marks can survive almost unchanged. A single crater may remain visible longer than entire mountain ranges on Earth. This is why crater counting helps scientists estimate the age of a surface. Older regions usually contain more overlapping impact marks. Younger regions appear smoother because ice, lava, or other material erased earlier craters. The method is not perfect, but it reveals broad chapters in a moon's history. There is no need to hold on to every detail. You can let the moons drift quietly through your mind. Our moon shows this contrast clearly. Its bright highlands are ancient and densely cratered. The darker plains, called Maria, formed later from vast flows of basaltic lava. Early astronomers thought these dark regions might be seas. Their names still preserve that peaceful misunderstanding. Mare tranquillitatis means the sea of tranquility. Mare imbrium means the sea of rains. There is almost no liquid water in these broad plains. They are frozen landscapes of dark volcanic rock. Long ago, large impacts broke through the lunar crust. Melted rock later rose from the interior and filled enormous basins. The lava cooled into smooth plains visible from Earth. Because fewer craters cover them, they appear younger than the surrounding highlands. The moon was once far more geologically active than it is today. Its interior held enough heat to produce widespread volcanism. Most large eruptions ended billions of years ago, yet some small volcanic features may be much younger. The moon did not become quiet all at once. Its activity faded gradually, like warmth leaving a stone after sunset. The far side contains fewer dark maria. Its crust is generally thicker than the crust on the near side. Lava had more difficulty reaching the surface there. This difference may be connected to the moon's early formation. Earth warmed the near side during the moon's youngest years. That uneven heating may have helped create different crustal thicknesses. A moon can preserve the influence of its planet within its own geology. The near side also contains more heat-producing elements in certain regions. These elements may have kept portions of the interior warm for longer. Their presence contributed to later volcanic activity. Even the familiar face of the moon is shaped by hidden chemical differences. If your eyes feel heavy, you can let them close. The story will keep moving softly in the background. Many moons always show nearly the same face toward their planets. This condition is called tidal locking. Our moon rotates once during each journey around Earth. Because both motions take nearly the same time, one hemisphere usually faces us. The moon is not motionless. It turns slowly as it travels around its orbit. Without that rotation, every side would eventually become visible from Earth. Tidal locking develops because gravity changes a moon's rotation over time. A planet raises small tidal bulges in the moon. If the moon rotates too quickly, those bulges are carried out of alignment. The planet's gravity pulls them back and gradually slows the rotation. Eventually, one rotation matches one orbit. This final arrangement uses less energy and remains stable. Most large moons in the solar system became tidally locked long ago. Europa keeps one side toward Jupiter. Titan keeps one side toward Saturn. Triton keeps one side toward Neptune. Pluto and Charon are locked to each other. Each would appear fixed in the other world's sky. Tidal locking does not create permanent daylight and darkness by itself. A locked moon still turns relative to the sun while orbiting its planet. Most locations experience day and night. The parent planet simply remains in nearly the same position overhead. Some places see it high in the sky. Others never see it at all. On the far side of our moon, Earth always remains below the horizon. There, the sky appears free from our bright blue planet. Radio signals from Earth are also greatly reduced. The landscape experiences long lunar days and nights. Sunrise moves slowly across the horizon. Each daylight period lasts about 2 Earth weeks. Then darkness returns for roughly the same length of time. Temperatures change greatly between sunlight and night. Yet below the surface, changes become gentler. A few meters beneath the ground, temperatures remain more stable. Future lunar shelters may use this natural insulation. Lava tubes could provide even deeper protection. These tunnels formed when ancient lava flows cooled on the outside. Liquid rock continued moving through the interior. When the eruption ended, empty passages remained behind. Some lunar lava tubes may be wide enough to contain large structures. Their ceilings could shield explorers from radiation and tiny impacts. An old volcanic tunnel may someday become a quiet refuge. The moon also experiences moonquakes. Some are caused by tidal forces from Earth. Others happen as the lunar interior slowly cools and contracts. A few are connected to meteorite impacts. There are also shallow moonquakes with uncertain origins. They can last longer than many earthquakes. The moon's dry, fractured crust does not absorb vibrations quickly. The shaking may continue as echoes move through the rock. Despite the name, most moonquakes are not violent global events. They are small movements within an old cooling world. Seismometers left by astronauts recorded thousands of them. The vibrations helped scientists study the moon's hidden layers. Waves travel differently through crust, mantle, and core. By measuring their paths, researchers can infer internal structure. The moon has a small metallic core. Part of it may still remain liquid. Its ancient interior is quieter than Earth's, but not completely still. Many other moons also experience internal vibrations. Tidal flexing may create quakes on Europa. Cracking ice could send waves through its outer shell. Enceladus may tremble as fractures open and close. Titan's crust may respond to tides raised by Saturn. A future seismometer could listen to these distant interiors. It might hear oceans moving beneath ice. It could measure the thickness of frozen shells. A quiet moon may tell its story to vibrations too small to see. There is no need to hold on to every detail. You can let the moons drift quietly through your mind. Some moons have surfaces that slowly change with the seasons. Triton's thin atmosphere grows partly from sunlight, warming frozen nitrogen. As seasons shift, gas may freeze in one region and return elsewhere. The atmosphere can therefore move across the moon over long periods. Pluto experiences a similar cycle. Though it is not technically a moon, nitrogen, methane, and carbon monoxide freeze and evaporate with changing sunlight. Charon's dark polar region may depend on material escaping during these cycles. Seasonal chemistry connects the two worlds. Titan's seasons are much longer than Earth's. Saturn takes nearly 30 Earth years to orbit the Sun. Each season on Titan lasts more than 7 Earth years. Clouds and rainfall shift gradually between hemispheres. Methane lakes respond to these slow atmospheric changes. Dunes near Titan's equator may also record prevailing winds. The moon's landscape is shaped by weather, even in extraordinary cold. Thin clouds have been observed above Titan's lakes and polar regions. Rainfall may arrive in rare but powerful events. Afterward, channels and darkened ground slowly change. Then the surface becomes quiet again beneath the orange haze. Neptune's moon. Triton may also carry seasonal frost patterns. Its southern hemisphere was receiving strong sunlight during Voyager's visit. Dark streaks extended across bright nitrogen ice. Winds may have carried particles from active plumes. Over decades, different regions received changing illumination. A future visitor may see a surface unlike the one photographed in 1989. Even a frozen moon is not always visually permanent. Iapetus changes brightness as it travels around Saturn. Its dark leading side faces the direction of motion. Its bright trailing side reflects far more sunlight. Early astronomers sometimes lost sight of it during part of its orbit. The moon seemed to disappear, then return again. This mystery was understood only after its two-tone surface became known. A moon's rotation can reveal its markings even across enormous distance. Other moons change brightness because of shape. An elongated moon presents different surface areas as it rotates. A tumbling object may brighten and fade in an irregular pattern. Astronomers use these light curves to estimate rotation and form. A moon, too small to photograph clearly, can still reveal its shape through light. Its changing brightness becomes a quiet message from the darkness. Surface color also provides clues. Fresh ice often appears brighter than old, weathered material. Radiation darkens some compounds over time. charged particles can break molecules apart and create new substances. Micrometeorites continually strike exposed surfaces. This gradual alteration is called space weathering. On our moon, it darkens and reddens the soil. Tiny impacts melt grains into glassy particles. Solar wind places hydrogen and helium into the upper surface. The ground becomes a record of constant exposure to space. Icy moons weather differently. Radiation can split water molecules into hydrogen and oxygen. Some oxygen remains temporarily near the surface. This helps create extremely thin atmospheres around moons like Europa and Ganymede. The molecules are so sparse that they rarely collide. Such an atmosphere is often called an exosphere. Earth's moon also has an exosphere. It contains tiny amounts of helium, neon, argon, and other gases. The particles travel long distances between surface contacts. There is no wind in the familiar sense. No breeze moves dust across the plains. Yet individual atoms continue their quiet journeys. Mercury has a similar type of exosphere, although it is a planet. Small worlds often cannot hold thick atmospheres. Their gravity is too weak, or their surfaces are too cold and exposed. Still, even a nearly airless moon is not surrounded by perfect emptiness. A few molecules can remain close to the ground. Io has a thin atmosphere made largely of sulfur dioxide. Volcanoes release gas from the interior. Sunlight also warms surface frost and turns some of it directly into vapor. When Io enters Jupiter's shadow, parts of the atmosphere may collapse as frost. When sunlight returns, some material becomes gas again. The atmosphere can therefore breathe with each eclipse. Its changes follow a repeated orbital rhythm. Callisto has a thin atmosphere containing carbon dioxide and oxygen. Ganymede has a faint oxygen atmosphere. Europa's exosphere includes oxygen created from surface ice. Rhea carries traces of oxygen and carbon dioxide. Dione may possess a very weak oxygen exosphere as well. These are not breathable skies. They are delicate collections of particles above silent ground. Titan is the great exception among moons. Its atmosphere is thicker at the surface than Earth's. A person standing there would experience significant atmospheric pressure. The low gravity would make movement feel light. A dense atmosphere and weak gravity allow objects to fall slowly. With suitable equipment, human-powered flight might even be imaginable. The air is mostly nitrogen, but oxygen is absent. Methane and complex organic haze color the sky. High above, sunlight drives chemical reactions. Simple molecules join into larger carbon-rich compounds. They drift downward as a fine organic mist. Titan's dunes may contain some of this dark material. The moon receives a constant, slow fall of atmospheric chemistry. Its surface is connected to its sky through rain, haze, rivers, and evaporation. Few forgotten moons possess such a complete weather system. If your eyes feel heavy, you can let them close. The story will keep moving softly in the background. Magnetic fields can also shape the environments around moons. Earth's moon does not have a strong global magnetic field today, but some lunar rocks preserve ancient magnetism. This suggests the moon once had a working internal dynamo. Motion inside its molten core may have generated a magnetic field. The field weakened as the interior cooled. Local magnetic patches remain within parts of the crust. Some create unusual bright markings called lunar swirls. Renner Gamma is one of the best known examples. It appears as pale, curling patterns on dark lunar ground. The markings are not raised mountains or deep valleys. They are differences in surface color and space weathering. Local magnetic fields may partially shield the soil from solar wind. Protected regions remain brighter than nearby ground. A vanished global field may therefore survive as delicate surface patterns. Ganymede still has a global magnetic field. Its field interacts with Jupiter's powerful magnetosphere. Charged particles move along invisible magnetic lines. Auroras glow near the moon's polar regions. The auroras shift as Jupiter's magnetic field changes around them. A salty underground ocean resists some of these changes. By observing the auroral motion, scientists inferred the ocean's presence. Light above the surface revealed water below it. Europa and Callisto lack strong internal magnetic fields, yet salty oceans can create induced magnetic responses. Jupiter's changing field produces electrical currents inside conductive water. Those currents generate secondary magnetic fields. Spacecraft instruments detect these subtle signals. A hidden sea becomes visible through magnetism rather than direct sight. The same technique may help study moons around Uranus and Neptune. If future spacecraft measure changing magnetic fields carefully, they may find buried oceans. A moon does not need to open its ice for us to know water is there. It can answer through gravity, auroras, rotation, and electrical currents. Sometimes several small clues point toward the same quiet conclusion. A moon may be much more active below than it appears above. Even completely frozen bodies can preserve warmth from radioactive decay. Rocky material contains unstable elements that release energy over time. Large moons retain this heat more effectively than small ones. Tidal forces can add further warmth. Chemical reactions between water and rock can produce additional energy. The final interior depends on size, composition, orbit, and history. Two neighboring moons may therefore develop very differently. Io became volcanic. Europa preserved an ocean. Ganymede formed a magnetic field. Callisto remained more ancient and only partly separated inside. They all circle the same planet. Their differences show how small changes can guide entire worlds. The same is true around Saturn. Mimas appears heavily cratered and inactive, yet may hide water. Enceladus releases fresh ice and vapor into space. Tethys carries enormous fractures. Dione may retain a deep ocean. Rhea remains quieter and more heavily cratered. Titan holds atmosphere, rivers, lakes, and perhaps a buried sea. Iapetus became divided into bright and dark hemispheres. Hyperion tumbles like a porous fragment. One planetary family contains many separate geological stories. Nothing needs to become perfectly clear. You can picture them simply as worlds with different textures. Some are smooth and pale. Some are dark, fractured, or softly covered with haze. Some hold oceans below ice. Others preserve craters older than nearly everything on Earth. Their surfaces receive sunlight, shadow, dust, and radiation. Their interiors cool at their own patient pace. Far away, Uranus's moons move through long seasons. Neptune's companions circle beneath faint blue light. Charon remains fixed above Pluto's distant plains. Tiny asteroid moons turn around bodies with almost no gravity. Each world carries time differently. Some erase old surfaces. Others remember almost every impact. And while those silent records remain beneath the stars, you can let your own thoughts fade. There is no need to study the markings or follow every orbit. The moons will continue keeping their ancient memories. Their ice will hold old fractures. Their rocks will keep traces of vanished fields. Their shadows will move slowly across distant ground, and you can rest while those forgotten worlds remain quietly awake. Some moons are known only through a few images, a measured orbit, and a faint point of reflected light. Their surfaces have never been seen in detail. Their colors may be estimated from distant observations. Their shapes may be inferred from brightness changing over time. A moon can remain mostly unknown even after its existence is confirmed. This is especially true for the outer irregular moons of the giant planets. They travel far from their planets on tilted and often stretched paths. Many orbit in the opposite direction from the planet's rotation. These backward orbits suggest that the moons were captured long ago. They probably formed elsewhere and later entered the planet's gravitational reach. There is no need to hold on to every detail. You can let the moons drift quietly through your mind. Jupiter has many distant irregular moons. Some belong to groups with similar orbits and surface colors. The Himalaya group travels around Jupiter in the same general direction as the planet rotates. Its members may be fragments of one larger captured object. Himalaya is the largest moon in the group. It is dark, irregular, and much smaller than Jupiter's 4 great moons. A faint ring of dust may follow a path connected with Himalaya. Impacts on small moons can release particles into surrounding space. The grains spread slowly along the orbit. A moon too small to become round can still create a structure millions of kilometers wide. Farther away, the Carme group follows retrograde orbits. The moons travel backward around Jupiter, as seen from above the planet's north pole. Their reddish colors and similar paths suggest a common parent body. That earlier object may have broken apart after a collision. The fragments now circle Jupiter as separate named moons. The Ananke group may have formed in a similar way. Its members occupy a wider range of tilted orbits. The Pacific group is more scattered and may have a more complicated history. Some members could come from different captured objects. Their paths overlap without forming one simple family. Distant moon systems are often untidy records of ancient encounters. Saturn also holds many irregular satellites. Phoebe is one of the most familiar because a spacecraft has visited it closely. It circles Saturn backward and far beyond the large regular moons. Its dark surface contains water ice, carbon-rich material, and many craters. Phoebe may have formed in the outer solar system. Saturn later captured it during an early period of moving planets and scattered debris. Its composition differs from moons that form near Saturn. Phoebe therefore carries material from another region into the Saturnian system. It is like a preserved traveler from colder and more distant beginnings. Other Saturnian irregular moons are grouped by orbital direction and inclination. The Inuit group follows prograde orbits. The Gallic group also travels forward, but along different tilted paths. The Norse group contains many retrograde moons. Their names come from several traditions and stories. The moons themselves are mostly tiny, dark, and unresolved. They may be fragments of several larger captured objects. Collisions among irregular moons could continue even after capture. Their wide orbital regions sometimes cross or approach one another. Over billions of years, rare impacts can create new families of pieces. A forgotten moon may be the remnant of another forgotten moon. If your eyes feel heavy, you can let them close. The story will keep moving softly in the background. Uranus has irregular moons with equally distant paths. Sycorax is the largest known member of this outer family. Its orbit is retrograde and strongly tilted. Caliban, Setebos, Prospero, and others follow similarly unusual routes. Their dark surfaces are difficult to study. Some observations suggest slight differences in color. These differences may reveal separate origins or later surface changes. Uranus's unusual tilt adds another layer to their motion. The planet's equatorial moons follow its sideways orientation. The irregular outer moons preserve paths shaped more by capture than by the equatorial disk. Two populations therefore circle the same planet in very different arrangements. The inner regular moons resemble a flattened family formed nearby. The outer irregular moons resemble scattered visitors gathered later. Neptune's distant moons tell a related story. NISO travels extremely far from Neptune. It takes many Earth years to complete one orbit. at its greatest distance, the moon moves through a region almost unimaginably remote from the planet. Yet Neptune's gravity still keeps it bound. Psamathe follows a similarly distant retrograde orbit. The two moons may be related fragments from one earlier captured body. Sao, Lamadea, and Halimede follow other wide and tilted paths. Halimede may share a surface color with Nereid. This has led to the idea that it could be a fragment broken from Nereid. The evidence is limited, but the possibility is gentle and intriguing. One distant moon may preserve a piece of another. Captured moons raise an important question. How does a planet hold an object that was once moving freely around the sun? A simple two-body encounter usually does not produce permanent capture. The incoming object gains speed as it approaches the planet. It often leaves with enough speed to escape again. Something must remove orbital energy. In the early solar system, several processes could do this. Gas surrounding a young planet might have slowed a small object. A collision could have removed energy. Three-body interactions could also allow one body to escape while another remained. A binary object may approach a giant planet. The planet's gravity can separate the pair. One member is thrown away. The other loses enough energy to become a moon. This process may help explain Triton's capture by Neptune. Triton may once have belonged to a binary pair in the Kuiper Belt. Neptune separated the pair during a close encounter. The companion escaped, while Triton remained behind. Its first orbit was probably highly elongated. Tidal forces gradually changed into the nearly circular path seen today. That adjustment released tremendous internal heat. Triton's interior may have melted deeply during the process. A captured object can be completely transformed by becoming a moon. The capture can also transform the planet's original satellite system. Triton's arrival may have destabilized many earlier Neptunian moons. Some could have collided. Others may have escaped. Debris may have formed new smaller moons later. The family seen today could be the quiet result of an ancient rearrangement. There is no need to hold on to every detail. You can let these old encounters soften into distant motion. Some moons may have exchanged places or migrated greatly after formation. Saturn's moon. Titan probably did not always orbit at its present distance. Tidal interactions gradually push it outward. Measurements suggest that Titan may be moving away from Saturn faster than once expected. This migration influences the entire moon system. As a moon moves, it can cross resonances with other moons. Those crossings alter orbital shapes and inclinations. They may create periods of stronger tidal heating. A moon that is quiet today may have been active during an earlier resonance. A moon active today may not remain so forever. Enceladus's internal heat could depend on the timing of its orbital evolution. Its ocean may have frozen and melted during different periods. Tidal fractures may open more strongly at some times than others. The current plumes are one chapter in a changing thermal history. Mimas may also have entered a state that allowed an ocean to survive. Its heavily cratered surface looks ancient. A buried ocean, if confirmed, might be geologically young. This would mean the interior changed without fully renewing the exterior. A moon can begin a new hidden chapter beneath an old surface. Jupiter's moons also migrated while the planet and its surrounding disk evolved. The Galilean moons may have formed from gas and dust around young Jupiter. Material spiraled inward through that disk. Early generations of moons might have fallen into the planet. Later generations survived as the disk thinned. Io, Europa, Ganymede, and Callisto may be among the final large moons formed there. Their composition changes with distance from Jupiter. Io is rocky and nearly without water. Europa contains more ice. Ganymede and Callisto contain still larger fractions of frozen material. Temperature differences in the ancient disk helped create this pattern. Closer to Jupiter, it was too warm for much water ice to remain. Farther away, ice could gather with rock. The moons became records of temperature around a young giant planet. Saturn's regular moons may also have formed in a surrounding disk. Titan collected enough material to become enormous. Smaller moons gathered nearer and farther from the planet. Some current moons may have formed later from ring material. The line between original moons and later generations remains uncertain. Saturn's rings may be young compared with the planet. They might come from a moon destroyed within the last few 100 million years. Another possibility is that the rings are much older, but continually renewed. Dust contamination and particle recycling complicate the estimate. If the rings came from a broken moon, that vanished world remains visible in countless icy pieces. The rings would be a moon spread into a flat, bright memory. Over time, parts of the ring may gather into new moonlets. Some moonlets may fall apart again. Creation and destruction can repeat near the Roche limit. A small body grows where gravity allows it, then collisions or tidal forces reshape it. The system remains delicate, but never completely motionless. The moon around Earth also continues to evolve. Its orbit is not a perfect circle. Its distance changes during each month. At perigee, it is closer to Earth. At apogee, it is farther away. Its apparent size in our sky changes slightly. Sometimes a full moon near perigee appears larger and brighter. The difference is real but gentle. The moon's orbit is also tilted relative to Earth's path around the sun. Because of this, eclipses do not occur every month. Most new moons pass slightly above or below the sun. Most full moons pass slightly above or below Earth's shadow. Only near certain crossing points can an eclipse occur. These points are called nodes. The nodes slowly move around the orbit over time. This creates repeating eclipse seasons. Ancient observers recognized long cycles in eclipse patterns. One of these is known as the Saros cycle. After a little more than 18 years, similar eclipse geometry returns. The eclipse does not happen in exactly the same place on Earth, but the arrangement of Sun, Earth, and Moon becomes familiar again. A celestial pattern can return after nearly 2 decades. It is another example of slow repetition written into orbital motion. The Moon also appears to wobble gently from Earth. This effect is called libration. Because the orbit is elliptical and the rotation remains steady, we can see slightly around the eastern and western edges. The Moon's tilted axis also lets us look a little beyond its northern and southern limits. Over time, about 59% of the lunar surface becomes visible from Earth. We never see all of it at once. The familiar face subtly changes from night to night. A little more of one edge appears, then another edge slowly returns. The Moon is tidally locked, but not perfectly still in our sky. Its gentle rocking reveals hidden margins. Other locked moons also experience libration. The amount of wobble can reveal internal structure. A solid moon and a moon with a detached icy shell may librate differently. Enceladus's measured libration helps support the idea of a global ocean. Its outer ice shell moves more freely than it would if attached directly to rock. The shell may slide above liquid water. A tiny change in orientation becomes evidence for an ocean beneath the surface. Europa's ice shell may also move separately from its interior. Surface fractures could shift over geological time. Some line patterns may have formed as the shell rotated slightly. The exact history remains debated. Yet a moon's surface can record movement between layers far below. Titan's rotation and gravity field also offer clues to its hidden ocean. If the crust is separated from the interior by a liquid, it responds differently to Saturn's pull. Spacecraft measurements help estimate these subtle changes. A distant ocean can be studied without drilling through ice. Gravity maps, magnetic fields, and rotation all become quiet instruments. Some moons contain mountains formed in unusual ways. On Earth, mountains often rise through plate tectonics. Most moons lack Earth-like moving plates. Their highlands may come from impacts, faulting, volcanic construction, or crustal deformation. Eos mountains are often not volcanoes. Many are large blocks lifted by compression in the crust. Volcanic plains spread around them. The combination creates landscapes unlike Earth's familiar ranges. On Iapetus, the equatorial ridge forms a long chain of peaks. Some rise more than 10 kilometers above nearby plains. If the ridge came from a former ring, countless particles once fell along the equator. If it formed internally, the crust must have responded in a highly organized way. Either explanation describes a world with a remarkable past. Miranda's cliffs in Coronai may have risen through internal convection. Warm ice could have moved slowly beneath colder layers. The surface broke into strange patchwork terrains. A small moon can create enormous topography if its ice remains warm enough to flow. On Pluto's moon, Charon, canyons divide broad regions. They may mark expansion as the interior ocean froze. The surface stretched because frozen water takes up more space than liquid water, and ocean's disappearance can build mountains and valleys above it. The missing water remains recorded in the crust. Impact basins also create high terrain. When a large object strikes, the surface rebounds. Central peaks rise inside many craters. In very large basins, multiple rings may form. Callisto's Valhalla structure contains broad concentric rings. They spread across thousands of kilometers. The pattern may have formed as the icy crust responded to a major impact. The rings resemble frozen ripples preserved in solid ground. Ganymede contains similar multi-ring structures. Our moon's Great Basins once had towering rims and central uplift. Later, lava partly buried many features. The remaining circular mountains still outline ancient impacts. A crater is therefore not only a hole, it is a complete landscape of rim, floor, fractured rock, and raised peaks. On small moons, one crater may dominate the entire body. Mimas carries Herschel, Proteus carries Pharos, Phobos carries Stickney. Each impact altered a significant part of the moon. The world survived because the collision energy remained below the point of complete disruption. Other bodies were not so fortunate. Some were shattered and reassembled. Their present forms may be loose collections of fragments. Saturn's moon. Pan has a low density and an unusual ridge. Atlas has a similarly delicate shape. These moons may be porous bodies coated with ring particles. They are less like carved stones and more like accumulated snowbanks in orbit. Their surfaces may be extremely soft and weak. A person could not stand there safely in any ordinary way. But tonight, they can remain distant and weightless. The story will keep moving softly in the background. You do not need to follow every family or every migration. Imagine only the slow gathering and scattering of small worlds. A captured moon arrives from far away. A ring spreads from a broken body. A moonlet forms from drifting particles. A resonance warms an ocean beneath ice. A tiny wobble reveals that the ocean is still there. The giant planets carry these quiet records around the sun. Jupiter holds families of dark captured fragments. Saturn gathers irregular moons from several ancient populations. Uranus turns sideways with inner moons and distant visitors. Neptune keeps Triton, perhaps the greatest captured moon of all. Beyond them, Pluto and Charon continue as a double world. Every system has been rearranged by time. Moons have moved outward, inward, together, and apart. Some have survived almost unchanged. Some have become rings, fragments, or hidden memories in another moon's surface. There is no need to decide which story is most important. You can let them all become one soft movement through the outer dark. The forgotten moons will continue along their tilted paths. Their faint surfaces will catch a little distant sunlight. And while their ancient families circle quietly, you can allow yourself to rest. Moonlight is never truly made by a moon. It is sunlight reflected from stone, ice, dust, cloud, or frozen gas. Each moon changes that light in its own quiet way. Fresh ice can return a great deal of sunlight to space. Dark rock may absorb most of it and reflect only a faint glow. This difference is described by a property called albedo. Enceladus has one of the brightest surfaces in the solar system. Its young ice reflects almost all the sunlight that reaches it. Phoebe, by contrast, is dark and absorbs much more light. From the same distance, the two moons would appear remarkably different. There is no need to hold on to every detail. You can let the moons drift quietly through your mind. A moon's brightness can reveal the age of its surface. Fresh material is often cleaner and more reflective. Older ground becomes darkened by radiation, dust, and tiny impacts. On Enceladus, bright ice near the south pole suggests recent activity. On Europa, younger bands cross older plains. On Callisto, ancient terrain appears darker and densely cratered. Color can also suggest what a moon is made from. Water ice often produces pale, cool tones. Sulfur creates yellow, orange, and reddish shades on Io. Organic compounds can deepen surfaces into brown, red, or charcoal colors. Radiation may transform simple molecules into increasingly complex materials. A quiet moon can become a laboratory beneath open space. No wind or rain is needed for chemistry to continue. Sunlight, charged particles, and time are enough. Europa's surface receives intense radiation from Jupiter's magnetic field. This radiation breaks apart water ice molecules. Hydrogen escapes more easily into space. Oxygen can remain near the surface or become trapped within the ice. Other chemical compounds may also form. Some could later be carried downward through cracks or slow crustal motion. If surface material reaches Europa's ocean, it may deliver useful chemical energy. The ocean might then receive ingredients from both rock below and ice above. This movement remains uncertain and difficult to measure, yet it offers one possible connection between the surface and hidden sea. Ganymede's polar ice appears brighter than its equatorial regions. Its magnetic field guides charged particles toward the poles. The particles alter and redistribute the uppermost ice. Magnetism therefore helps paint broad patterns on the surface. Callisto's dark ground contains scattered bright spots. These may be small exposures of cleaner ice. Impacts can uncover fresh material beneath an older dark coating. Over time, the exposed ice slowly changes again. A moon's colors are never completely permanent. If your eyes feel heavy, you can let them close. The story will keep moving softly in the background. Our own moon changes appearance through phases rather than changing shape. Half of the moon is always illuminated by the sun. From Earth, we see different portions of that bright half. A new moon lies near the direction of the sun. Its illuminated side faces mostly away from Earth. As the moon moves along its orbit, a thin crescent appears. The bright portion grows to first quarter and waxing gibbous phases. At full moon, the near side is almost completely illuminated. Then the visible light gradually decreases again. The cycle takes about 29.5 days. This period shaped many early calendars. People watched the moon to measure months, seasons, and ceremonial time. The word month is connected historically with the moon. A small world in the sky helped organize human memory. Earthshine sometimes illuminates the dark part of a crescent moon. Sunlight reflects from Earth onto the lunar night side. The faint glow reveals the full round shape behind the bright crescent. From the moon, Earth would pass through its own phases. A nearly full Earth would shine especially brightly in the lunar sky. Oceans, clouds, deserts, and ice would all contribute reflected light. Because Earth appears larger than the moon appears to us, it would dominate the view. On the lunar near side, it would remain in nearly the same region of sky. It would shift slightly because of libration, but it would never cross from horizon to horizon. Future observers might watch Earth's clouds change beneath a fixed blue globe. The far side would remain without that view. Its sky would contain only stars, the sun, and occasional visiting spacecraft. Other moons experience phases as seen from their planets. The Galilean moons appear as tiny disks through telescopes. They brighten, darken, disappear into shadow, and cross Jupiter's face. Saturn's large moons also move through changing illumination. Titan's atmosphere scatters light around its crescent edge. When viewed from behind, its haze forms a glowing ring. Sunlight passes through high atmospheric layers before reaching a camera. This reveals the height and complexity of the haze. A moon's atmosphere can become most visible when the surface itself is dark. Plumes can also appear clearly against darkness. Enceladus's jets are often easier to observe when backlit by the sun. Tiny ice particles scatter the light. The hidden fountains then become bright curtains rising above the surface. Some discoveries depend simply on looking from the correct direction. A world may seem quiet until light reveals what was already there. There is no need to remember every phase or angle. You can let the light move slowly across the moons. Moon dust behaves differently from familiar dust on Earth. Without air, grains do not drift in ordinary breezes. They rise after impacts, land after long arcs, and cling through electrical forces. Lunar soil is called regolith. It is made from broken rock, glassy fragments, and extremely fine particles. Billions of impacts have crushed the surface gradually. Because there is no flowing water, many grains remain sharp and angular. Astronauts found that lunar dust clung strongly to suits and equipment. It carried a distinctive smell into their spacecraft. The smell was sometimes compared with burned powder. The scent did not exist on the airless moon itself. It appeared only after reactive dust entered the cabin's atmosphere. Sunlight can electrically charge dust grains on airless worlds. The solar wind also adds charge, near the boundary between daylight and darkness. Electrical conditions may change quickly. Some grains could briefly lift above the surface. A faint horizon glow was reported during early lunar missions. Similar dust movement may occur on small asteroids and moons. On Phobos, weak gravity allows impact debris to travel widely. Some particles may leave the moon completely. Others circle Mars before returning to Phobos or reaching Deimos. Dust can connect separate moons across shared space. Saturn's small moons constantly exchange dust with the rings. Particles strike their surfaces at low speeds. Some settle gently and build soft ridges. Others escape and join the surrounding ring material. Pan and Atlas may carry layers of extremely loose particles. Their shapes partly record where that material accumulated. The same grains can be moon, ring, and moon again across time. Around Jupiter, dust from Metis, Adrastea, Amalthea, and Thebe feeds faint rings. These rings are far darker than Saturn's bright ice. They are difficult to see except from special viewing angles. The moons quietly replace particles lost to sunlight and planetary gravity. A ring can survive because its moons continue shedding tiny pieces. Some moons share nearly the same orbit. Saturn's, Janus and Epimetheus exchange paths every few years, but other co-orbital relationships are even more delicate. Tethys travels with Telesto and Calypso near stable gravitational positions. Dione travels with Helene and Polydeuces. These smaller bodies are called Trojan moons. One remains ahead of the larger moon. The other follows behind. They occupy regions where gravitational forces create long-term balance. From above Saturn, the three moons would form a wide triangle. They travel together without needing equal size. Polydeuces does not remain at one exact point. It slowly wanders around its stable region. This motion is called libration, though it differs from lunar libration seen from Earth. The small moon follows a stretched loop around an invisible balance point. Gravity allows gentle motion without letting it escape. Trojan relationships may exist around planets throughout the galaxy. Jupiter possesses large groups of Trojan asteroids. They travel near stable positions ahead of and behind the planet. A giant exoplanet might also gather Trojan worlds. Some could be as large as moons or small planets. They would share the planet's orbit around a star, yet they would remain far ahead or far behind the planet itself. Such objects blur the meaning of moon, asteroid, and companion. Nature does not always follow the categories people create. Some moons may also share orbits due more complex patterns. Saturn's rings contain tiny moonlets embedded within them. These bodies create propeller-shaped disturbances. The moonlet itself may be too small to see directly. Its gravity pushes ring material aside. The resulting pattern reveals the hidden object. Thousands of such propellers may exist in the rings. Each could mark a body only hundreds of meters across. They are moons in the smallest and quietest sense. They do not clear complete gaps. They disturb only the particles close to their paths. Their traces move slowly with them around Saturn. Some have been followed for years through repeated images. A moonlet becomes known through the pattern it leaves behind. The same idea may apply to unseen moons elsewhere. A narrow ring edge may suggest an undiscovered shepherd. A repeating wave may reveal a hidden gravitational source. A sudden gap may preserve the orbit of something too dark to photograph. Scientists often learn about moons through their effects rather than their images. This is also true beyond the solar system. An exomoon might reveal itself by pulling gently on its planet. A transit could occur slightly early during one orbit. The next could happen slightly late. The moon and planet would be moving around a shared center of mass. Their timing would contain the moon's invisible rhythm. A very large exomoon could also cross the star separately. It might produce a small additional dimming. But stars are not perfectly steady. Dark star spots, bright regions, and instrumental noise can imitate these patterns. Several proposed exomoons remain uncertain for this reason. Scientific caution keeps them in the category of candidates. Uncertainty does not make the search less beautiful. It simply means the story is still being written. There may be moons around worlds unlike anything in our solar system. Hot, giant planets orbit very close to their stars. Their moons might be unstable because the star's gravity is strong. Some may have lost their moons during inward migration. Others may never have formed large satellites. Giant planets farther from their stars may offer calmer environments. They could possess families resembling Jupiter's or Saturn's. Young planets might be surrounded by disks where new moons are forming. Astronomers have observed possible disks around forming exoplanets. Within such disks, dust and gas may gather into future satellites. A moon system can begin as a miniature version of a planetary system. The young planet acts like a small central world. Material circles it in a flattened disk. Particles collide gently and begin to grow. Moonlets form, migrate, merge, or fall inward. Only some survive after the disk disappears. Far away, this process may be happening now. New moons could be forming around planets still warm from birth. Their surfaces may be molten or covered with deep magma oceans. Over time, they will cool into rock and ice. Some may capture atmospheres. Others may lose almost everything to space. The final result depends on distance, size, and the parent planet. Large moons around giant planets may be common. A moon the size of Earth is physically possible in some systems. Such a world could hold an atmosphere for billions of years. It might possess continents, oceans, clouds, and changing seasons. Its parent planet would fill a large part of the sky. The planet's reflected light could brighten the moon's nights. Regular eclipses might bring periods of deeper darkness. Other moons would appear, moving around the same planet. A sky like this would feel crowded and peaceful at once. A habitable moon would face challenges unknown on Earth. Radiation from the planet's magnetic field could be intense. Tidal heating might become too strong or too weak. Frequent eclipses could alter climate. Orbital resonances might change internal activity. Answers. Also, yet these same effects could also help. Tidal heat might maintain liquid water far from the star. A magnetic field could protect the surface. A thick atmosphere could spread heat between day and night. A nearby giant planet might shield the moon from some impacts, or it might redirect other objects toward the system. There is no single, simple answer. Habitability depends on many conditions working together. A moon may be suitable for life without resembling Earth closely. It could hide life beneath ice. It could support floating organisms in a dense atmosphere. It might contain warm seafloor environments beneath a frozen crust. Even within our solar system, moons have expanded the idea of a habitable place. The traditional search once focused mainly on planets near comfortable starlight. Europa and Enceladus revealed another possibility. Gravity itself can become a source of warmth. A world can remain active beyond the usual habitable zone. Its ocean may never see sunlight, yet it can persist beneath ice for immense spans of time. Titan offers a different lesson. Complex chemistry can continue at extremely low temperatures. Its lakes are not made from water. Its atmosphere produces organic molecules in great abundance. It may resemble an early chemical laboratory more than a living world. But it shows that moons can sustain complete environmental cycles. Rain falls, rivers flow, Dunes migrate and lakes change. The materials are unfamiliar, yet the patterns feel gently recognizable. Some exomoons may combine several of these qualities. They could have surface oceans and strong tides. They might also have hidden seas beneath polar ice. Their skies may glow with auroras from the parent planet. Volcanoes could release gases into thick atmospheres. Ring shadows might move across their surfaces. Distant companions could rise and set in unusual directions. No telescope has shown us such a place clearly. For now, these moons remain possibilities shaped by known physics. You can let them remain soft and unfinished. There's no need to decide whether they are inhabited. Simply imagine that the galaxy may contain more moons than planets. Every giant world may carry several companions. Every small moon may hold a separate history. Some will be dry and cratered. Some will be volcanic, oceanic, hazy, or covered in clean ice. Many will never receive names from any observer. They will circle beneath unfamiliar stars without needing to be discovered. Closer to home, forgotten moons continue leaving subtle signs. Dust rises from airless ground. Fresh ice brightens fractures. Trojan companions rest near invisible balance points. Tiny moonlets carve propeller shapes through Saturn's rings. Farther away, possible exomoons pulled gently on distant planets. Each influence is small. Together, they fill the universe with quiet motion. You can let the details dissolve now. Picture moonlight moving across pale ice. Picture dark dust settling onto an ancient crater floor. Imagine a small moon traveling beside a larger companion through Saturn's wide shadow. Beyond the solar system, another moon may be crossing a distant star. Its presence may appear only as a brief change in light. The world itself remains unseen. Still, it continues along its orbit, and while those hidden moons move beneath their patient stars, you can rest. Their reflected light will fade softly into the background. Their gravity will keep working without sound, and the forgotten worlds will carry the story gently onward, far from the bright planets. Many moons spend most of their existence inside darkness. They receive only brief visits from sunlight, spacecraft, or distant human attention. Some were discovered in photographs taken for completely different reasons. Others appeared years later when old images were examined again. A faint point moves slightly between one frame and another. That tiny motion revealed a world following a planet through space. There is no need to hold on to every detail. You can let the moons drift quietly through your mind. Discovering a moon often begins with patience rather than dramatic observation. Astronomers photograph the same region of sky many times. Stars remain nearly fixed, while nearby objects slowly change position. The smallest moons may move only a few pixels between images. Their light can be weaker than the glow surrounding their planets. Computer processing helps remove glare and compare repeated observations. Even then, a possible moon must be followed for months or years. Scientists need enough measurements to show that it truly orbits the planet. A single photograph can suggest a moon. A long series of photographs confirms its quiet path. Some moons have been lost after discovery. Their early observations were too limited to predict their future positions accurately. Astronomers knew the objects existed, but could no longer find them. Years later, improved telescopes sometimes recovered these missing satellites. The moon had never disappeared. Only our knowledge of its orbit had become uncertain. A recovered moon receives a more reliable path and a clearer identity. There is something peaceful in finding a world twice. The solar system did not lose it. It simply continued moving beyond the reach of an old calculation. Several small moons of Jupiter and Saturn experience this kind of temporary loss. Their distant, irregular orbits made predictions difficult. The gravity of the Sun and nearby planets slowly altered their paths. Long gaps between observations allowed uncertainties to grow. Modern surveys now watch wider areas with greater sensitivity. They can recover old moons and discover new companions in the same images. Many newly found moons are only a few kilometers wide. From Earth, they appear as faint points against darker space. Their shapes, mountains, and craters remain completely unseen. We know them through movement alone. If your eyes feel heavy, you can let them close. The story will keep moving softly in the background. A moon does not always need to circle a planet for billions of years. Some orbits remain stable only for limited periods. The Sun continuously pulls on every planetary satellite. Nearby moons also disturb one another. Small changes accumulate across enormous spans of time. A distant, irregular moon may slowly change its orbital tilt. Its path can become more stretched or more circular. In some cases, the orbit may eventually become unstable. The moon could escape and return to an independent path around the Sun. It might also collide with another satellite or its planet. These possibilities unfold so slowly that the present system still appears calm. Every moon we see is part of a temporary arrangement. Some arrangements last longer than the age of the solar system. Others survive for only a short chapter of cosmic time. The region where a planet can hold moons is called its Hill sphere. Inside this broad area, the planet's gravity can dominate over the Sun's pull. The size of the Hill sphere depends on the planet's mass and solar distance. A massive planet far from the Sun can hold moons across a wide region. This helps explain the great distances of some outer satellites. Neptune's farthest moons travel millions of kilometers from the planet. They remain bound because Neptune is massive and sunlight is weak there. Earth's Hill sphere is much smaller than Jupiter's or Neptune's. Our moon travels comfortably inside it. Temporary satellites often enter and leave near its outer boundaries. A moon orbiting too far away may be pulled free by the star. A moon orbiting too close may face strong tidal forces. Between these limits lies a broad region where long companionship is possible. Around exoplanets, the same rules should apply. A planet close to its star has a smaller region for stable moons. This may make large satellites rare around hot Jupiters. A giant planet farther out could hold a much richer family. Its moons might orbit across millions of kilometers. Some could follow regular circular paths. Others may travel backward like captured moons around our own giant planets. The parent star would still shape the outer limits of every orbit. Even forgotten moons remain connected to the wider system. Their planet holds them close. Their star sets the boundary of that hold. The galaxy carries both planet and moon together. There is no need to remember the name of any boundary. You can imagine only a wide, invisible shelter around each planet. Inside it, small worlds continue circling. Near the planet, gravity is strong and the orbits are quick. Farther away, the paths become larger and slower. At the edge, the star begins to pull more strongly. A moon may remain there for ages, balanced between two greater influences. Some moons are protected by their direction of motion. Retrograde satellites can remain stable farther from a planet than prograde satellites. Their backward movement changes how solar gravity disturbs their paths. This may partly explain why many very distant moons travel retrograde. The direction that seems unusual can sometimes provide greater stability. Orbital mechanics often creates balance in unexpected ways. A moon can survive by moving differently from the rest of its family. Small satellites also occupy narrow, safe regions between larger moons. Their paths may be shaped by repeated gravitational encounters. A slight change could send them into a collision or a different orbit. Yet many remain stable because resonances prevent dangerous approaches. The solar system contains countless examples of this quiet organization. Gravity does not create stillness. It creates repeating motion that avoids chaos for long periods. Some moons may be hiding inside planetary rings. Saturn's rings contain many temporary clumps of particles. Most spread apart after a short time. A few may be held together by their own weak gravity. These clumps can behave like tiny moonlets. They gather material, lose material, and leave patterns behind them. Their boundaries are not as clear as the boundaries of solid worlds. A small ring body may exist between object and structure. It can become more moon-like when particles collect. It can return to the ring after a collision. The moonlets, named She-2009S1, and similar tiny bodies are difficult to study. They may be only a few hundred meters across. Their shadows or disturbances sometimes reveal them more clearly than their surfaces. A body this small has almost no recognizable horizon. Its gravity is barely strong enough to hold loose material nearby, yet it still follows an orbit and shapes the particles around it. The definition of a moon becomes gentle at such small scales. There is no sudden line between dust, moonlit, and moon. Nature moves gradually from one form to another. If your eyes feel heavy, you can let them close. The story will keep moving softly in the background. Moon formation also occurs gradually. Around a young planet, dust grains first collide and stick together. Tiny particles become pebbles. Pebbles gather into larger clumps. Gravity becomes more important as those clumps increase in size. Some collide softly and merge. Others strike too quickly and break apart. A forming moon competes with neighboring bodies for material. It also interacts with gas in the surrounding disk. That gas can change the moon's orbit. Some young moons migrate inward and disappear into the planet. Others move outward or become trapped in resonances. The survivors become the mature moon system. Jupiter's current large moons may be the final generation from this process. Earlier moons could have formed and fallen inward. Their material became part of Jupiter or returned to the disk. The moons we know may therefore have forgotten predecessors. Those vanished satellites left no visible surfaces. Their existence is inferred from models of the young planetary system. Saturn may also have lost several generations of inner moons. Ring material and tidal migration can repeatedly rebuild small companions. A moon may form near the ring edge. It then moves outward, while new material gathers behind it. Several moons could be created in sequence. Their sizes may increase with distance from the ring. Some researchers study whether Saturn's inner moons form this way. The idea remains active and uncertain. Yet it shows that moons need not all share one birthday. A planetary family can contain ancient members and much younger rivals. Titan may be almost as old as Saturn. A small moon near the rings could be far younger. Both circle the same planet today. Their shared location does not require a shared history. Earth may also have possessed smaller temporary moons after the giant impact. Debris around the young planet did not gather instantly into one body. Many fragments probably collided and merged. Some may have orbited for a time beside the growing moon. Eventually, most were absorbed, scattered, or destroyed. The final moon carries material from that crowded beginning. Its present isolation hides an earlier family of fragments. Several theories suggest the moon formed through multiple impacts rather than one. Each collision could have created a small disk and a temporary moonlet. These moonlets might later have merged into the moon. The leading explanation still favors one major impact. but the precise details remain under study. Lunar rocks continue to refine the story. Their chemical similarities with Earth are especially important. The Moon shares many isotopic patterns with Earth's mantle. This suggests extensive mixing during formation, yet subtle differences preserve clues about impact temperature and material origin. A moon's beginning can remain readable inside individual crystals. Zircon grains from lunar samples are extremely ancient. Some formed more than 4 billion years ago. They survived impacts, volcanism, and long exposure to space. Their chemistry helps estimate when the lunar crust began to solidify. The early moon may have been covered by a global magma ocean. As the molten material cooled, minerals crystallized and separated. Lighter minerals floated upward. They formed the first pale crust. Denser minerals sank into the interior. The bright lunar highlands still contain rocks from this ancient process. Quiet, white landscape can therefore be the remains of a molten world. Similar magma oceans may have existed on other large moons. Giant impacts and rapid formation release enormous heat. A young moon can begin almost completely melted. Cooling then creates layers, crust, and sometimes a metallic core. Water and other volatile materials may escape or become trapped. The final moon depends on how quickly it cools. Small moons lose heat rapidly. Large moons retain warmth for much longer. Ganymede's layered interior reflects its great size. Callisto's less separated structure may reflect slower or incomplete differentiation. Two similar moons can follow different thermal paths. Their present interiors preserve choices made billions of years ago. There is no need to hold on to every detail. You can let these beginnings become warm light fading into cooler worlds. Some moons may have formed from the remains of other moons. Saturn's moon family could contain fragments from major collisions. Uranus's inner moons occupy a crowded region where future impacts are possible. Computer models suggest some orbits may eventually cross. A collision could create a temporary ring. The ring might later gather into new moons. The names would change, but the material could remain. A future Uranian moon may be built from several current ones. This lies far beyond any human lifetime. For now, the moons continue along their close and careful paths. Mars may also repeat cycles of rings and moons. Phobos is slowly approaching the planet. If it breaks apart, the debris may spread into a ring. Some material could fall onto Mars. Some could later gather beyond the Roche limit. A new small moon might eventually form. Mars could therefore alternate between having rings and moons. Its current companions may be one stage in that long cycle. The same material can appear as a moon, then a ring, then another moon. A planetary system recycles itself through gravity. Neptune's capture of Triton may have created a debris disk. Destroyed earlier moons could have spread material around the planet. Some of that debris may have gathered into present inner moons. Their smooth, regular orbits contrast with Triton's captured origin, Naiad, Thalassa, Despina, Galatea, Larissa, and Proteus may be second-generation bodies. They could have formed after the original system was disrupted. Their existence may be a quiet recovery after ancient disorder. A moon family can rebuild itself. Small fragments settle into a disk. Collisions become gentler. New bodies gather on circular paths. The final arrangement looks peaceful, even if its origin was complicated. Pluto's small moons may also be products of debris. Their bright water-ice surfaces connect them with Charon. A giant impact could have spread material around Pluto. Charon formed from the largest portion. Nix, Hydra, Kerberos, and Styx gathered farther out. Their current resonances may have developed as Charon slowly migrated outward. The small moons were carried into new orbital patterns. Their unusual rotations show the continuing influence of the central binary. A moon system can remember its formation through resonance and spin. Even when surfaces become cratered, motion preserves history. Orbital positions are another kind of fossil. They reveal migration that happened long before observation. The story will keep moving softly in the background. You can let each orbit become a faint circular line. Some circles grow slowly outward. Others shrink inward. Some exchange places without touching. Some tilt, wobble, or turn backward. Each path records energy shared between worlds. Moons also influence how planets appear from great distance. A large moon can make a planet wobble slightly. Future telescopes may detect this motion around nearby stars. The wobble could reveal that the planet has a massive companion. Direct images might one day separate a planet from its largest moon. Their light would blend at first. Repeated observations could show two objects circling together. Spectroscopy might reveal different atmospheres or surface materials. A giant planet could show methane and hydrogen. Its moon might show water, oxygen, or carbon dioxide. The combined light would contain both worlds. Separating their signals would be difficult but possible with advanced instruments. A distant moon could even affect interpretations of a planet's climate. Reflected light from the moon might change with phase. Its transits could slightly alter brightness measurements. An atmosphere around the moon could add unexpected chemical signatures. What appears to be one world may sometimes be a blended system. Astronomers must learn to recognize planetary families across interstellar distance. Our own Earth and Moon would also appear blended from far away. Earth is much brighter, but the Moon would shift the system's overall light and position. During certain phases, it would contribute more reflected light. A distant observer might eventually detect its presence. They could infer ocean tides or rotational effects only with much greater information. To them, our moon might also be a forgotten moon. It would be one faint companion beside a small blue planet. No craters or maria would be visible. No one would know its familiar face. They might only see a periodic signal, yet the moon would still shape Earth's oceans and history. A world does not need to be understood to remain important. Some X-moons could orbit planets that no longer orbit stars. Rogue planets travel freely through interstellar space. They may have been ejected from young planetary systems. If such a planet carried moons before ejection, some could remain bound. The planet and its satellites would travel together through darkness. There would be no sunrise from a nearby star. Tidal heating and internal radioactivity might provide the only warmth. A thick atmosphere could trap some internal energy. A moon with an underground ocean might remain liquid for long periods. The system would be dark, but not necessarily inactive. A giant planet could glow faintly from its own heat. Young rogue planets are especially warm. Their moons might receive infrared light from the planet. Auroras could move through magnetic fields. Volcanoes or plumes might continue beneath a starless sky. Such moons are difficult to detect. Rogue planets themselves are usually found only through gravitational lensing or faint heat. Their moons would be smaller and even more hidden. Still, the laws of gravity allow them. The galaxy may contain moon systems moving between stars. They would be forgotten not only by observers, but by daylight itself. You do not need to imagine that darkness as empty. Picture a warm giant planet glowing softly in infrared. Around it, small moons move through a deep, quiet night. One carries ice, another contains rock and hidden heat. A third may release faint plumes into space. The entire family travels together without a nearby sun. Their orbits provide the only regular measure of time. A moon completes one journey, then another begins. Nothing marks the years except repeated motion. Closer to home, the sun still reaches every known moon. Even at Neptune, its light remains visible. At Pluto, it can cast shadows across mountains and ice. At the farthest irregular moons, it still reflects from dark surfaces. The light may be weak, but it is not absent. Each forgotten moon returns a small portion toward space. Some of that light eventually enters a telescope near Earth. A few photons travel for hours before reaching an instrument. They carry information about color, motion, and composition. From those faint signals, scientists rebuild the presence of a world. A tiny moon becomes known through reflected sunlight and patience. You can let that light grow softer now. Imagine it leaving a dark, irregular surface. It travels past the giant planet and across the outer solar system. Much later, it reaches a mirror on Earth. For one brief moment, a forgotten moon appears as a point, then it continues along its orbit, whether anyone watches or not. The young moons, the lost moons, and the rebuilt moons all keep moving. Some form from disks, some form from impacts, some form from the remains of older companions. Far beyond them, possible moon systems travel between stars. Their stories are not finished. There's no need to follow where every path leads. You can allow the circles to widen and fade. The moons will remember their origins in rock, ice, and motion. Their planets will hold them through another quiet orbit. And while those faint worlds continue beneath the darkness, you can rest. As the journey begins to quiet, the moons continue moving beyond our attention. They do not pause when telescopes turn away. They do not become less real when their names are forgotten. Across the solar system, they remain beside their planets. Some move through rings of ice and dust. Some travel above hidden oceans, sealed beneath ancient crusts. Others follow wide, tilted paths far from the worlds that captured them. There is no need to hold on to every detail. You can let the moons drift quietly through your mind. Jupiter still turns beneath its broad bands of cloud. Close beside it, Io continues its warm and restless orbit. The moon bends slightly under the pull of gravity. Deep inside, rock softens and moves. Across the surface, old lava cools, while new material quietly appears. Farther away, Europa carries its ocean beneath pale ice. The water does not need sunlight to remain part of the story. Jupiter and the neighboring moons provide a slower kind of warmth. The frozen shell rises and falls by small amounts. Cracks open, close, and shift across geological time. Below them, the ocean may touch a rocky floor. Minerals may enter the water. Chemical reactions may continue in complete darkness. No one knows whether anything lives there. The uncertainty can remain open and peaceful. Ganymede circles farther out, larger than every other moon. Its magnetic field continues creating a small protected region inside Jupiter's greater field. Auroras move above its poles. Their gentle changes reveal the water hidden beneath the crust. Callisto follows beyond it, carrying one of the oldest visible surfaces nearby. Crater rests upon crater. Some edges have softened through immense time. Others remain bright where newer impacts expose cleaner ice. The moon preserves a history that Earth has mostly erased. Rain, oceans, wind, and moving continents renew our planet. Callisto remembers almost everything. You do not need to remember it with Callisto. The moon can hold its own history. Around Saturn, countless fragments travel through reflected sunlight. The rings appear smooth from far away. Up close, they are made from separate pieces. Some are as small as dust. Others are large enough to resemble houses or hills. They move together because gravity guides their individual paths. Tiny moons create waves across the rings. Some open narrow gaps. Others gather particles along their equators. Pan continues through the Anka Gap. Atlas remains near the edge of the A-ring. Daphnis raises delicate waves from the ring plane. Prometheus draws pale streamers from the F-ring. Each small moon changes something much larger than itself. Enceladus still sends ice into space. The grains rise above the South Pole and spread along Saturn's orbit. Some become part of the E-ring. Some fall back onto the moon. Others reach neighboring worlds or the planet itself. A buried ocean quietly replenishes a ring around a giant planet. The connection is so large, yet it begins through narrow fractures in ice. Titan moves through orange haze beyond the brightest rings. Methane clouds may gather above its distant lakes. Rain may fall onto dark shorelines. Rivers may briefly carry a liquid across the frozen ground. Then the landscape becomes quiet again. Beneath the surface, another ocean may remain hidden. Titan holds water below and hydrocarbons above. One moon carries two completely different liquid worlds. Farther from Saturn, Iapetus turns through light and shadow. Its dark side absorbs warmth. Bright side returns more sunlight to space. The equatorial ridge remains across its middle. It may be the remains of a vanished ring. It may have risen from the moon's interior. The answer is still waiting. Hyperion continues tumbling nearby. Its rotation is uncertain, but its orbit remains bound. Deep craters cover its porous surface. Dark material rests in their floors. The little moon turns without choosing one face to show Saturn. There is no need to hold on to every detail. The story will keep moving softly in the background. Uranus continues around the sun while lying almost on its side. Its rings and regular moons follow the same tilted plane. Miranda carries cliffs and broken-looking regions across its small surface. Ariel keeps long valleys in its bright ice. Umbriel remains darker and older. Titania and Oberon preserve canyons, craters, and possible oceans below. Only one spacecraft has seen them closely. The images came from a brief passage through distant winter light. Since then, the moons have completed many silent orbits. Their surfaces remain largely unmapped. Their interiors are known only through careful models and faint measurements. A future visitor may discover plumes, young ice, or hidden seas. It may also find worlds quieter than expected. Both possibilities can remain together tonight. Neptune moves farther into the dim outer solar system. Trident circles backward above the blue planet. Its captured orbit remembers an earlier life beyond Neptune. Nitrogen frost covers the surface. Seasonal sunlight changes the atmosphere. Dark streaks remain where plumes carry material across the ice. Triton may also hide an ocean beneath its frozen exterior. Even a captured moon can preserve warmth for billions of years. Nereid follows its long, stretched path. Proteus turns beneath the shadow of its great crater. Naiad and Thalassa continue their careful orbital dance. They approach without meeting. Gravity keeps their timing in balance. Farther out, Neso takes years to complete a single orbit. For most of that journey, Neptune is only a distant blue presence. The moon still belongs to it. A gravitational bond does not need closeness to remain real. Mars carries two small companions through the reddish sky. Phobos travels quickly above the surface. Its orbit slowly lowers. Deimos follows much farther away. Its dusty ground softens the shapes of ancient craters. Neither moon is large enough to become round. They resemble dark fragments left beside a planet. Their origins remain uncertain. Perhaps they were captured. Perhaps they formed from debris around Mars. Perhaps earlier moons came before them. Mars may have carried rings and satellites through several different ages. The present moons may be only the latest pair. Earth also travels with a moon formed in a distant beginning. Its pale highlands and dark plains remain visible tonight. The familiar pattern changes slightly with each phase. A thin crescent becomes a brighter curve. The curve grows until the near side is filled with sunlight. Then the light slowly withdraws again. The moon keeps nearly the same face turned toward Earth. Yet libration reveals small regions around its edges. It appears to rock gently during the month. The motion is slight, still. It reminds us that tidal locking is not complete stillness. Everything continues moving. The moon pulls on Earth's oceans. Earth's oceans respond with tides. The planet's rotation transfers energy into the lunar orbit. The moon slowly moves farther away. Earth's days become slightly longer. Neither change can be noticed during a single night. But across deep time, the relationship evolves. Planets and moons do not simply remain together. They shape one another while they travel. The moon may have helped stabilize Earth's tilt. Its tides influenced coastlines and shallow seas. Its changing light guided human calendars. Its cycles entered stories, navigation, farming, and quiet nights. Long before anyone understood its origin, people noticed its return. It disappeared into darkness and slowly became bright again. That repetition made the sky feel measurable. A distant world became part of ordinary life. Beyond Neptune, Pluto and Charon continue their shared rotation. Each keeps one face toward the other. Charon remains fixed above one region of Pluto. From the opposite hemisphere, it never appears at all. Nix, Hydra, Styx, and Kerberos tumble around the central pair. Their shapes are irregular. Their surfaces are bright with ice. Their motion preserves the influence of two central worlds instead of one. Farther away, Dysnomia follows Eris. Hiaka and Namaga circle Haumea. Small moons accompany asteroids throughout the solar system. Some formed after impacts, some separated from rapidly rotating bodies. Some may be loose collections of stones, barely held together. A moon does not need mountains, atmosphere, or a round horizon. It needs only to remain gravitationally bound. Even that definition becomes soft, near rings, and temporary captures. A clump of particles may behave like a moonlet. A small asteroid may circle Earth for several years. A fragment may share our path around the sun without becoming a true satellite. The categories help people organize what they observe. The objects themselves simply follow gravity. If your eyes feel heavy, you can let them close. The moons do not need to remain clear. Their names can become soft sounds moving through the background. Some moons have been discovered, lost, and discovered again. Their faint light disappeared into the uncertainty of old calculations. Years later, astronomers found them in a new region of sky. The moons had continued circling throughout the silence. Human attention came and went. The orbit remained. Many distant moons are still known only as moving points. No camera has shown their landscapes. No instrument has measured their internal layers. They may carry craters, cliffs, dust, or exposed ice. They may be fragments from larger bodies broken apart long ago. Several may share one origin without ever meeting again. Jupiter's distant moon groups continue along related paths. Saturn carries families of prograde and retrograde companions. Uranus holds scattered visitors far beyond its regular moons. Neptune keeps faint satellites near the edge of its gravitational reach. Each group is a memory written in orbit. The original bodies may be gone. Their fragments remain as a quiet family. Moons can disappear in other ways. A moon may move inward until tidal forces pull it apart. Its fragments may spread into a ring. The ring may later create new moonlets. Another moon may migrate outward until the star's gravity removes it. A collision may scatter pieces into independent paths. A captured moon may disturb an older system and force earlier companions away. The present solar system is only one moment in this long exchange. The planets once carried different moons. They may carry different moons again. This does not make their systems unstable tonight. It simply gives every orbit a history. Some histories began in disks around young planets. Dust and gas moved in circles. Small grains met and joined. Pebbles became larger bodies. Moonlets collided, merged, or fell inward. Several generations may have formed before the final moon survived. Other histories began with impacts. A collision placed material into orbit. The debris formed a ring around the damaged world. Within that ring, gravity gathered a companion. Earth's moon may have begun this way. Charon and Pluto's smaller moons may have similar origins. Other moons began as independent objects. They traveled around the sun before a planet captured them. Triton may be the greatest example. Phoebe may be another captured traveler. The irregular moons around giant planets probably include many more. A moon's present home does not always reveal its birthplace. It may carry chemistry from another region of the solar system. It may hold ice formed much farther from the sun. Its surface can preserve a journey that happened before its orbit began. Beyond the solar system, the forgotten moons become even more numerous. Planets circle other stars in great variety. Some are giant worlds close to their suns. Others move through long, cold years. Young planets remain surrounded by dusty disks. Within those disks, moons may be forming now. No confirmed exomoon has yet become a simple, unquestioned discovery. The signals remain delicate. A transit occurs slightly early. A planet's light curve contains an additional dip. A possible companion changes the timing or duration of the crossing. The pattern may be caused by a moon. It may also come from the star or the limits of measurement. For now, the distant moons remain uncertain. They do not need confirmation to be imaginable. The same physical laws operate around other stars. Large planets should gather material. Impacts should create debris. Gravity should capture, organize, and reshape smaller worlds. Some exomoons may be icy and quiet. Some may be warmed by tidal forces. Some could hold thick atmospheres. Others may circle planets with rings far larger than Saturn's. A moon might see its parent planet covering much of the sky. Cloud bands could stretch above the horizon. Storms might remain visible for months. The planet's reflected light could brighten the moon's night. Eclipses would bring long shadows at regular intervals. Other moons might appear as moving lights around the same giant world. A distant moon could hide an ocean under ice. Another could carry a surface sea beneath a thick atmosphere. A third might be volcanic, warmed by resonant companions. The patterns found near Jupiter and Saturn may repeat throughout the galaxy, but each system would arrange them differently. Some moons may circle rogue planets between the stars. Their worlds would receive no ordinary sunrise. The planet's remaining warmth might provide a faint infrared glow. Tidal forces could keep internal oceans liquid. Auroras might move above dark surfaces. The entire moon family would travel together through interstellar night. No nearby star would define the year. Time would be measured only through rotation and orbit. A moon would pass behind its planet, then it would return. One quiet cycle would follow another. There is no need to imagine every distant world. You can let them become small lights moving beyond the edge of thought. The forgotten moons are not forgotten by gravity. Their planets continue pulling them inward. The moons pull back in return. Some raise tides in oceans. Some stretch ice until it warms. Some guide ring particles into narrow bands. Some carry dust from one world to another. Some leave auroral footprints in a planet's atmosphere. Others preserve ancient surfaces without changing them. A moon can be small and still matter. It can be dark and still shape a ring. It can be frozen and still hold an ocean. It can be unnamed and still follow a perfect orbit. It can remain unseen and still pull on a planet. There is no need to hold on to every detail. You can let the moons drift quietly through your mind. Imagine the solar system growing dimmer now. The sun becomes a soft point beyond the outer planets. Jupiter continues beneath its pale reflected light. Saturn carries its rings through the darkness. Uranus turns sideways with its quiet moons. Neptune moves slowly beneath a deep blue atmosphere. Pluto and Charon revolve around the space between them. Smaller moons follow at every distance. Some are round, some are stretched, some are no larger than hills. Their surfaces catch a little light, then return to shadow. Europa passes beneath Jupiter's night. Enceladus releases a faint veil of ice. Titan's orange atmosphere hides the stars. Triton moves backward around Neptune. Phobos crosses the Martian sky. Charon remains above Pluto, our own. Moon continues beyond the window, whether visible tonight or not. Nothing is asking for your attention now. The oceans beneath the ice will remain there. The rings will continue turning. The small captured moons will follow their wide paths. The distant candidates around other stars can remain unresolved. You do not need to search for them. You do not need to remember where each journey began. Let the names grow quieter. Europa, Enceladus, Titan, Triton, Ganymede, Callisto, Miranda, Charon. Then let even those names drift away. The story can continue without words. Only the slow motion remains. A moon moves around a planet. The planet moves around a star. The star moves through the galaxy. And the galaxy travels through a universe filled with quiet distance. Your breathing can remain easy and unmeasured. Your thoughts do not need to complete themselves. Anything unfinished can wait beyond this night. The forgotten moons have carried their secrets for billions of years. They can carry them a little longer. You can release the last images now. The cracked ice can fade. The orange clouds can soften. The rings can become thin lines of distant light. The planets can disappear gently into darkness. There is nothing more you need to follow. The story will keep moving softly in the background, and somewhere far away, a small unnamed moon completes another orbit. No one watches it pass through shadow. No one hears it move. It simply continues, held by gravity beneath a distant star. You can rest in the same quiet rhythm. There's no need to hurry towards sleep. You can let it arrive in its own time. The moons will keep moving. The night will remain around you. And everything can become still.